हेलो 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 हाँ ठीक है ना इस पर हेलो
अभी भी नहीं है। बोलो
हेलो हेलो
इधर तो दिखा रहा
हेलो
है।
थोड़ा ग्लिंच आएगा ना यहाँ से थोड़ी लेट हेलो
आ गया। ओके
आ गया आ गया
ठीक है करो।
आ गया
Okay. Thank you.
ठीक है करो। हाँ हाँ चलेंगे इधर से। ये तो इधर इधर से करो। ठीक हाँ ठीक हाँ हाँ नहीं नहीं कुछ नहीं हटा दो बता दो। हाँ उसमें हाँ उसमें यूट्यूब पे देखने में आएगा। सब कुछ
Everything fine? Should we wait for 2 more minutes? Let me see here. 5, 9, 11. Oh, we are pretty good. Oh, yeah. You have just reshuffled a little bit the seats here. So, good morning to you all. Thank you again for coming back. Fourth day now. God, this is indeed quite a bit of a marathon here, especially for you. I was yesterday a little bit slower in the program than I according to schedule, but I think it's okay because we can make up some things I want to cover. Actually, tomorrow we can do this a little shorter. But I would like to go back just very briefly to this idea which we discussed yesterday. And this is this idea that if you coordinate a substrate to your catalyst, if that gets irradiated and if it's doing a homolysis, this can be a starting point for the for a radical reaction. And I think the chemistry which I showed you in the end was that we can apply this principle to nitroalkanes, especially to these nitroesters, which are very easily deprotonated, forming an anion. And then this anion, I think I had it even on a previous slide here. These anions can, once you make the anion such a copper-2 complex, can then be very easily oxidized. And again, it might be just a homolysis of that copper-oxygen bond, which makes copper-1, and then the radical, and use this for a starting point. And the other thing which we discussed was that these type of homolysis reactions can be very fast. And I would like to go back to this idea as well and just show you a few more examples for this. But before we start, how about you guys? Did you ever run photoreactions? So let me know. You see here, it's still the same number from yesterday because it's still the same presentation. So how is it for you? Did you do something in this regard? With some of you I talked during the tea breaks, and they told me a little bit what they were doing. How is it with you in general? Okay. Okay. Not relevant for my project. You never know. But that's okay. And it should be clearly seen that photocatalysis is not solving all the problems you might have in a synthetic project, but it's a very good technique to have around. And the same will also be true. I would like to discuss with you in the second part today, I would like to discuss with you some electrocatalysis reaction. And it's the same thing. It's good to have it around. And nowadays it makes it relatively easy because you can have these kits which you can very easily store, but then also build up an electrochemical reaction and get started on this. Okay, so it looks like it's about mix. Some of you have done it, some of you have not done it, but maybe you will do it at some point, and that is absolutely fine. Let me tell you one thing which we did and which relates again to this idea that these homolysis reactions are very fast. And so we were wondering if these homolysis reactions are that fast, then maybe we can use not just copper, maybe we can use iron. And we did something very simple here. We used iron 3 chloride as a means to make, oh, wait a minute, where do we have the pen somewhere? Excuse me. Ah. Oh, great. Thank you. Thank you. Okay. So we started asking a very simple question. Can we take iron 3 chloride, I draw it down here. Let me see if it lets me do it. And if this gets irradiated, and you can see we have to do this because we don't have a ligand here. We have to do this in the at lower wavelengths. But again, the LEDs for 365 are around. And so we were simply asking the very simple question, if we do this, can we generate chlorine radicals out of this? And this would involve a reduction of the iron 3 to the iron 2. And we were interested in doing this for the one reason that obviously iron catalysis might be very promising if you do this. And if you think about this, so far I would say there are not so many reactions around you can really catalyze with iron. A lot of the reactions you mediate with iron. Best known is the reduction of nitrobenzene to aniline. That has been done on a technical scale with iron or iron 3 chloride in order to make from with iron. Not with iron 3 chloride. It's done with iron in order to make from nitrobenzene to make aniline, right? But there are not so many reactions which are really catalytic. And so we were wondering if this is helping, or this could be a starting point for us here. And you can see what we are ultimately doing. We have done a hydrogen abstraction from aldehydes, and we are utilizing, and again you can look this up in the bond dissociation tables. We were utilizing that the carbon-hydrogen bond on an aldehyde is weaker than the carbon-hydrogen bonds like in an alkyl chain or so. So that gave us a very good indication that we should be able to do this selectively. But the other thing which we also were hoping to achieve or consider, and this is why we choose aldehydes, is iron 3 chloride might not only be a source for a chlorine radical, but iron 3 chloride is a pretty good Lewis acid. And we all know that Lewis acids can coordinate with carbonyl compounds. And we were wondering what this if that would have a beneficial effect on the activation of these aldehydes. And indeed, it does. We had some calculations. We had some collaborations with a group in Chile, and they did calculations, and they calculated various complexes of the aldehyde with the iron 3 chlorides. It's something you can see here, maybe not too clearly. And they indeed calculated that the bond dissociation energy of that carbon-hydrogen bond should be lowered, and quite a bit lowered, by about almost 7 kcal per mole through the interaction with the iron Lewis acid. And that also helped us probably to understand is that when we used for the same chemistry copper 2 chloride, we talked about this yesterday, this was the initial observation by Kochi that you can generate the same chlorine radicals also from copper 2 chloride. But we saw that this works with much lower yields, so that the iron process was more effective. And so we were doing this, and then again you see here we are generating iron 2, and this is why I would like, and maybe I had a tutorial question for this, but maybe we can do this now and come back to this nevertheless a little bit later in a slightly different context. So when we make these acyl radicals, then by the hydrogen abstraction, in the same process we are making from iron 3, we are making iron 2. And so we had to think about what we can do in order to bring then eventually in this process to bring this back to iron 3. And so that was the reason. In principle, this could, we go through the mechanism in a moment, in principle, this could, according to the reaction mechanism, happen by itself. But we found out that if you add an organic co-catalyst, and this is what we did here with this diphenylanthracene, that this reoxidation path, this reoxidation is much more effective. And so this is why you see here that we're using a combination of 2 compounds, the iron 3 chloride and the diphenylanthracene, and we would propose that we also go through 2 photocatalytic cycles. And let me show you this. And so what we think is we have an iron photocatalytic cycle, and we have a photocatalytic cycle which comes from this anthracene molecule. And so in the iron photocatalytic cycle, what should happen is that we excite the iron 3 chloride, and again we had a chloride source in there, so we had probably an equilibrium of FeCl3 and FeCl4 minus. And then once this is excited, it can dissociate a chlorine radical, and then at that point it becomes iron 2. And so now the chlorine radical can do the abstraction from the acyl radical. This acyl radical, and again, this will become a little bit more important in a moment, because I will show you a second way to make such acyl radicals. But this acyl radical is nucleophilic. This is always known. The radical is not, there's no electron withdrawing capacity from the carbonyl group because it's orthogonal. The pi orbitals of the CO bond are orthogonal to the radical center, and essentially the phenyl group, and it works like a donor. So it's known these radicals are nucleophilic, and therefore they should react with electrophilic alkenes, and this is indeed what they are doing. And so once we do the addition, then we go and have this radical here, and then this radical, in order to close the catalytic cycle, if this radical gets reduced, let me do this here. So if this gets another electron, we would go through this carb anion, and if this picks up a proton, then you get this compound. And in principle, this electron it could come from the iron 2 chloride. If the iron 2 chloride gets oxidized, it would give away one electron and would go back to the iron 3 chloride. But we found that this is not so effective. And therefore, we found that it is more effective to have an electron, an photocatalyst in there, which might do this mediation more effectively. And that is that's why we are using this diphenylanthracene, because when you excite the diphenylanthracene is very easily able to oxidize the iron 2 to the iron 3 back, and then you're forming such a radical anion here, right? This molecule from the excited state takes one electron from the iron 2, makes such a radical anion, and this radical anion is a very strong reductant, and this is ultimately reducing the radical, makes this anion, which then gets protonated and finishes the reaction. And so this is a classical Giese reaction. That is the name or Giese reaction comes from the person who has invented this, not photochemically, but Professor Giese from Germany, and then later on he was in Switzerland. He developed a lot of radical chemistry in the thermal way, and especially such reactions where you add radicals to alpha-beta unsaturated alkenes, and this way these type of reactions became known as the Giese reaction. And so this was one way how we could make iron work catalytically. And then we used actually the same type of principle with just a different precursor. Not just with an aldehyde, we also used such trioxanes. And these trioxanes, it's the pretty much same idea that first of all, they're quite easily to come by because it's essentially the trimerization of an aldehyde. And that can occur under acidic conditions. And in fact, the trioxane for R equals hydrogen, that is commercial. And this is actually an equivalent to formaldehyde, right? So we could have used formaldehyde, but to use this trioxane is actually even more convenient. Formaldehyde is a gas, or you have it in an aqueous solution, but the trioxane is a pretty good alternative if you want to use formaldehyde. And so what this does here is, again, it has a hydrogen atom which is privileged to be deprotonated, because you see, once you do this, and not deprotonated, that's the wrong term, need to be precise here, so where the hydrogen abstraction could be occur. That's what I should have said. Because if this happens, we have seen yesterday that radicals which have in the neighbor position have an heteroatom like an oxygen are especially stable. And so this radical has even 2 oxygens next to it. So we felt that this should work. And now we did the same type of chemistry. Again, we used iron 3 chloride. And in this case, we're again using an anthracene. I don't really know. We tried this, and my co-workers were assuring me that in this case, the dicyanoanthracene worked better for them. And you see in the previous example, they used diphenylanthracene. From the potential tale, so it should have been similar. I was not sure if it is, you see, this was the publication came out 2 years later, and it's 2 different co-workers. So sometimes it's also co-worker dependent, right? Which type of system they like. But it's very similar. So the reaction conditions are very similar. And again, the radical you're generating here is again nucleophilic. And so consequently, it will react with electron deficient alkenes. And so that is one of the things where the limitation is with this reaction, but also with the direct activation to the alkenes, we have not been able to add this to even styrenes, which usually are good acceptors, right? But it was only working with electron deficient alkenes. And I would like to tell you about that problem a little later as well. But the polarity always has to match, and even with styrenes, these nucleophilic radicals, it seems not to match any longer. And I nevertheless will tell you that there might be ways to go around this. And so then in this case, if we are again able to get these type of adducts here, you can isolate them, but you don't have to. And then if you heat this up a little bit, so we're doing this at room temperature, but if you heat this up, for example, in a microwave, then in the first step, the iron is the photocatalyst, the iron 3, but then you can also utilize the properties of iron 3 as a Lewis acid. And you can see here you have an acetal, and acetals are deprotected to the carbonyl groups by Lewis acids or by Bronsted acids. And so you can see if we are doing this, we have overall added a formyl group to our alkene, right? So we have added essentially hydrogen and an aldehyde to these two centers. And clearly, and I'm not pretending that this can rival in any way the industrially used process of a hydroformylation, which is very broad and is being done on million-ton scale. But nevertheless, it is a formal hydroformylation which is iron catalyzed. And let me just remind you. All right. Let me just remind you of the hydroformylation. Here. Right. The hydroformylation is one of these reactions which is really fantastic in terms of atom economy, making no waste. And so the hydroformylation was this reaction where you add across the double bond, where you add hydrogen and carbon monoxide, and you need a catalyst for this. The catalyst can be either a rhodium-1 catalyst or a cobalt-0 catalyst, and then your product, typically, with a few exceptions, are the hydroformylated product where the aldehyde group is on the terminal end. And as you can see, this is, I think, in the beginning when this chemistry was developed, this was in the 1930s, there they used cobalt as a catalyst, and later on they found out that rhodium is much more effective, but of course also much more expensive. And so I think these days, depending on the company, they use both types of catalysts, and they, and again, this is done really on tremendous scale, so our process clearly cannot compete with this, but nevertheless we do a hydroformylation of electron deficient alkenes, iron catalyzed. Just let me remind you or ask you about this reaction. I'm not sure how familiar you are. So typically you get this onto the terminal position, and this is true when this is an alkyl group. Are you familiar with that reaction? Do you know also what substrates will give you the aldehyde group on this position? Have you learned about this in any of your other reaction or lectures? Because it's useful to know. So usually it wants to go terminal, because whenever you have, like, for example, you have like a rhodium carbonyl hydrogen complex, which might have ligands on here, if this adds to the double bond, for steric reason, it wants to add, it wants to do something like this, right? It wants to add the hydrogen to the smaller substitute, to the smaller side, and then the big rhodium fragment with its ligands around this, it wants to add it to the terminal side. So that's steric reasons. And then if it is doing the reductive elimination, it will go through such a rhodium acyl complex where it has where the carbon monoxide has been inserted, and then it will get hydrolyzed and form the aldehydes here. The situation changes. This is the one, I think, the one class of alkenes you should remember. There are a few more which give the branched products, but especially styrenes give you the branched product. And the reason for this, so let me just point out what it gives you. So here the hydrogen adds to the terminal position and the aldehyde goes to the internal position. And the reason for this is that the arene substituent so if I have my alkene here, let me see that I draw this well. The reason is that your catalyst can also coordinate with can also get an additional coordination to the phenyl group. And then this way, the addition of the rhodium fragment will be directed to the, it will be directed to the internal position, right? So it coordinates with the phenyl ring, hydrogen adds, and then the rhodium is adding here. And so this is the one exception you might want to remember. And this is, of course, also quite interesting. This gives you the opportunity, and this has been done. If you have chiral ligands, this gives you an opportunity to develop asymmetric hydroformylation chemistry. And so, and these type of compounds are, of course, quite interesting, because if you convert the aldehyde group to the carboxylic acid by an oxidation, and if you're not using the simple styrene, if you're using all right. Yeah, wait a minute, I have one carbon too many here. So if you start with the I put this wrong. It should be here. It should be like it is here. I'm not sure how I can erase with this this compound with this pen here. Do you know which compound this is? Anybody ever taken it? This one, the product. That's ibuprofen. So if you have a headache, it's something you might do. And I don't think it's synthesized by hydroformylation chemistry. It's done in a different way, but hydroformylation would be a possibility. And then I don't know if I'm not sure how this is here in in India, if you buy what you buy, do you buy ibuprofen, just ibuprofen as a racemate, or do you buy the enantiomerically pure compound? Because the enantiomerically pure compound is, in the S enantiomer, is more effective. It's an interesting story. The R enantiomer actually makes a headache, and the S enantiomer relieves you from the headache. So if you take the racemate, but the S enantiomer is about 20 times more effective to kill the headache than the R enantiomer, which will give you the headache. And in addition, our body is transforming the R enantiomer into the S enantiomer. Don't ask me why, because evolution probably didn't know about ibuprofen, but it definitely works this way. And this is one interesting strategy from pharmaceutical industry these days. The ibuprofen patent was long gone, but since the realization these days is that we should not market racemates any longer as drugs, that you always have an advantage if you take an enantiomerically pure compound, simply for the fact that then you only have one compound in your body, and if you have two compounds in the body, then the other compound might have undesired side effects which you don't want to have. And there have been some very dramatic examples in the literature. If you ever want to read up on thalidomide, for example, that's the classical example where one enantiomer had a pain relieving effect, and the other one would cause burst effects if you would have taken it during pregnancy. And so then these days, if you now market the S, the enantiomerically pure compound, you can get a new patent, or you can get new patent extension. That is what is called, if you read it up in the literature, this is called the chiral switch, meaning you switch from racemic pharmaceuticals which are in the market to enantiomerically pure one, and then you can apply again for an extension. You will not get the full patent. You will not get another 20 years or so. You get less, but it's an incentive from the governments to make this more interesting. And so check the next time you're in a pharmacy. You probably can buy both. The one is called just ibuprofen, and the other one is called S-ibuprofen. And the S stands for the chiral center for the S configuration. And of course, it's more expensive, right? As you probably can imagine, right? So again, so we've been able to do this type of hydroformylation. Let me see where it was. So it was here, and then what we liked about this is that we can also install the carboxyl groups right away, because if we heat it up under oxygen, we will oxidize the aldehyde automatically. And if you use a substituted trioxane, for example, the methyl variant here, you can also do a hydroacylation. And so again, as I said, this is a small contribution to carbonylation chemistry, which cannot compete with the industrial used hydroformylation processes, but nevertheless, I think it's a good step to show what iron can maybe do. And so here are some of the examples which you will have in the handouts, and then we actually could do both processes together. So we could first do a hydroformylation, generate an aldehyde by using the trioxane. So we showed this on the vinyl sulfane, on the vinyl sulfone here, and you can see we're doing this reaction, the photoreaction with iron. Then we deprotecting with iron to generate the aldehyde. And then we utilize this first chemistry I showed you, that we can now in a second photoreaction activate the aldehyde and react it with a second alkene in order to get these two compounds, two alkenes stitched together through a carbonyl group. And everything is iron, right? So we do the two photochemical steps with iron, and we do the deprotection with iron. And again, I think that is something which might point to the fact that iron can actually also be an interesting metal for catalysis. So again, nucleophilic radical, these acyl radicals, these radicals we get from the trioxane, will react to electron deficient alkenes. And of course we tried at least styrene. And you know, then you get always, my coworkers always got this good advice from me as a advisor, and they say, try an electron deficient styrene, right? To do the styrene which has some electron deficient groups. Didn't work. We couldn't really do it. It was for maybe even various reasons why that would not work, but we were unsuccessful. But then, and that's the last story I want to tell you about this copper and iron chemistry. Again, new co-workers, and they said, maybe we do it again with copper, and maybe we generate the acyl radicals not by a hydrogen abstraction, maybe we generate it from an acid chloride. And so again, this is the one issue I would like to point out, that new slide here. Come on, let me do it. Okay. That you can generate the same type of radicals by different photocatalytic processes, right? And so the first one I showed you is that we would use the aldehyde, generate a chlorine atom, utilize that the bond dissociation energy is the weakest in this aldehyde, and then by abstracting the hydrogen, from the acyl radical. But the alternative to this is that you could start with an acid chloride and then do with the copper 1 photocatalyst. That is something we have seen yesterday quite a bit, to do a reduction. So copper 1 goes to copper 2, and you are forming the acyl radical, and in this case you're extruding chloride. So both times it's the same radical, but in the second case we would be able to take just about any R group here, and we would be able to add the acyl radical to the alkene, and suddenly everything worked. Styrenes worked, unactivated alkenes worked, didn't really matter. And one of the reasons we believe, again, which helps us here, is that we have this synergistic action from the copper 2, right? We are generating from copper 1 to copper 2, and so you can think about that we are generating some kind of a copper chloride, and this copper chloride complex, which still had ligand on there, so we were using I show you about this, I talk about this ligand in just a moment, but this is probably very rapidly, maybe even simultaneously, interacting with the radical, entraps it and stabilizes it. And then by a reductive elimination, you see we are getting a different product, of course, now. So now we are getting the product which had the chlorine molecule in there, and in the reaction before we had the hydrogen in there. But again, as I say, this worked with any alkene suddenly, and we believe it is because we have an interaction either in this way, that the radical attacks directly the copper, or that the radical abstracts from our metal salt directly the chlorine atom. And that is apparently so effective and runs probably maybe almost in a concerted way, that we are much broader in the type of alkenes we can use. So again, the take-home lesson maybe for all of us is that sometimes if we want to do a certain reaction where we want to add a radical across a double bond, we should think about different ways to make that. And I showed you this yesterday also with these nitroalkyl radicals. You could do it oxidative or reductively. And here you have a possibility to do this either by an electron transfer or by a hydrogen atom transfer process. And I would like to point out something else, which, and I must say again, this is, was very, very hard work from, you can see here probably from the name, is two of my Indian co-workers. Tirtha Mandal, he came with a European project as a postdoc, and then Mangesh Ghosh, who started his PhD in my group. And so they worked both really, really hard on this. Because in the beginning, we've been using a lot of these copper phenanthroline complexes, which I showed you, and they didn't work for this chemistry. And then they found out that these heteroleptic complexes, that they work very nicely. And they are also very easily formed, because when you mix a copper 1 salt, like copper chloride, when you mix this with a phenanthroline and the phosphine, 1-to-1, these heteroleptic complexes form very selectively, and you're not forming the homoleptic complexes. And so they found out about this, and initially we thought, okay, this is working because it has a very strong reduction power. So here it is minus 1.64. That was clear that this is enough for the copper for the acid chlorides, and then put the arrow on the wrong one. And then they also, these complexes have very long excited state lifetimes, and so initially we thought that this long excited state lifetime is needed for this type of transformation. But on the other hand, we had done many other reactions, ATRA reactions, which does the copper phenanthroline type ligand. So why didn't it work here? And why are these heteroleptic complexes so good? Okay, good oxidation and reduction potential, and also long excited state lifetimes. But we found out something else here, and that is, I think I should get a new page here. Oh, interesting. If I discard it, I erase it. Okay. And the one thing we notice, and this might be in general the interaction of these heteroleptic complexes, is if you have a heteroleptic complex which has two types of ligands on there, this is what you can easily prepare, and this is a copper 1 complex. But if you irradiate this in the presence of your acid chloride, copper 1 does really prefer to have phosphine ligands on there. And so what happens is, if you're irradiating this with in the presence of the acid chloride, it will form such a dimer. And then here you have presumably your cation still here. So if this is a copper 1 complex, we had like an anion here, BF4 minus. And so if we make the stoichiometric equation, then it would look like this. And you can see the interesting thing what happens. It's losing the nitrogen ligand. It's not losing the phosphine ligand. And that was something for us which was not obvious at that point. We looked in the literature, and there was a paper from Greg Fu, which we talked yesterday about these nucleophilic substitutions. And he, in one of his nucleophilic substitutions, noticed the same thing. And he pointed that also out, that the copper 1 coordinates with the phosphine. But then once you do the electron transfer, so once this goes then to, you reduce formally your acyl chloride, and so you might now make the acyl radical, and you go to copper 2, And what happens is it exchanges the ligand again. The copper-2 coordinates the nitrogen ligand. Copper-2 doesn't like phosphine. Copper-2 likes nitrogen. Copper-2 is more electrophilic, phosphine soft, copper-2 hard. If you look in the literature, that's then what we did. We checked, are there any copper-2 phosphine complexes known? And there are some papers which describe it from the 70s and 80s. And so I asked my coworker, and I say, can we prepare one so that we have a comparison and can do it? And they said it's not working. We cannot do it. We can do copper-1 phosphines. We cannot do copper-2 phosphines. So probably these literature reports are not correct. And this is an interesting interaction, how the mode of action might be. So it's not the heteroleptic complex which is doing the chemistry, but it's the copper-1, as long as copper-1, it's the copper-phosphine complex. If it's copper-2, it's the copper-nitrogen complex, which then also stabilizes and then indeed might give us the chemistry which we always would propose, is that these copper-2 phenanthroline complexes can interact very well with radicals. And so we thought that this is an interesting, really interesting finding, and this is probably the success that this reaction works so well. So you have it then again in the handouts, you have it here again, right? So you start with the heteroleptic complex because this is easily prepared, but then once you have in the presence of a chloride source, like your acid chloride, copper-1 phosphine complex, which forms is on copper-1, and then after the electron transfer, the phosphine ligand exchanges for the nitrogen ligand. And we could show this by NMR, we could show this by EPR in quite a number of ways. And here you see, and I really very much appreciate this from Bangladesh and Theater. You see, they have an amazing number of examples and very meaningful examples. Let me point this also out. Okay, I don't have it on. Don't have it on this slide. But what they did is, and that's also something very often which you find in papers, when you read papers and they say, we have 50 examples. The question is, how meaningful are the examples, right? Sometimes you have an aromatic ring, and then you put para-methyl, para-t-butyl, para-ethyl, and so on. These are not really meaningful examples. And so currently also the journals, many journals say, don't give us 50 examples, give us 10 examples, but the 10 examples should be meaningful. So you should have activated alkenes like vinyl arenes. Beside the phenyl, maybe heteroatom, some functional groups in there, electron-rich, electron-poor, have unactivated alkenes, have different substituents, so have terminal alkenes, 1,1 substituted, 1,2, 1,3, and so again, we tried all this, and the only alkenes this protocol doesn't work are tetra-substituted alkenes. It's probably understandable because they become sterically very hindered, but even tri-substituted alkenes still work. Show that it is compatible with functional groups. And so Mangesh and Tirta showed that you can have epoxides in your alkenes. You can have boranes in the alkenes, halides, alcohols, amines. So they showed a very, very broad scope. And so indeed, in the end, there 100 examples came out. And then the other thing I liked very much is they are both very, very ambitious. And so they had already a good number of examples. And I said to them, I think this is a great paper, we should publish this. And what do you think? We submit this to Anguman, to Jax, because I thought that's pretty cool. And they said, no. We need a better journey. So I would not have dared this. And they said, no, tell us what to do. We need to submit this to, and then they settled on Nature Catalysis. And I told them, this is a long shot. And again, it is a very, very long shot because we submitted this paper in September. And then it took like 4 weeks until the editor decided that it goes out for review. Then after 6 weeks, the first review reports came back. They were all positive, 3 review reports. But then they raised questions, especially to the mechanism. And again, Tirtha and Mangesh wanted to go back over Christmas to India, and he said, I'm not leaving. I need to do revisions now. And I convinced him, I said, we are able to do this until Christmas, so then you should still leave. And they were working day and night in the lab. And on Christmas Day, 24th of December, I filed the revisions. And 2 months later, the review reports came back, and they had sent it to a fourth reviewer, because we had a new X-ray structure in there, and they said now we need to ask an expert in X-ray crystallography if your structure is good. And then this reviewer came back and had the first three reviewers said it's great, it can be published, but the fourth reviewer had again a few questions, and he had new questions, right? And so again, Tirtha and Mangesh said, okay, we close our eyes, we do everything this reviewer wants to do, and again push this through. And the paper got accepted yesterday. So it was 6 months essentially what it did. And sometimes you have to try. Sometimes it will not work, absolutely. You have to balance this. We had the feeling that with 100 examples, with really extensive mechanistic studies, we have a chance. And still, even up in the very end, I was not sure it would work. But if you don't try, it will not work. And that's what I think told you earlier. I review a lot of PhD theses from India, and there is very, very, very good chemistry in there. And it is very often undersold. You publish it in good journals, but not in top journals. And you, together with your supervisors, you should always ask yourself, what can we try? And you, of course, also we don't do this. We don't submit papers to high impact journals where I know we don't have a chance. But we very often try to see what can we do in order to bring it there, to have a chance. And then with journals like Angewandte or JACS, it works maybe in 3 cases out of 10. It's still, rejection rates are high. But I believe you should try. And as I say, a lot of the chemistry I see coming from Indian labs are really good about this. And so here, this would be essentially our conclusion, right? We have 2 different protocols where we make acyl radicals, but with the one protocol where we do the homolysis starting from iron 3, we can also do it from iron copper 2, but copper 2 is not as effective. We can engage the acyl radicals, but we can only do it with electron withdrawing alkenes. And then the other protocol from the acid chlorides, where we have the copper 2 then to assist the process in radical stabilization, this allows us essentially to go through the whole range of alkenes. Okay, so this was the one thing I wanted to say. We have coffee tea break at 11? At 11, okay, so then I think this was the last. Last slide I had here. Okay, then I just give as a teaser, because we have 5 more minutes. I give you as a teaser the next chapter I want to discuss with you. And the next chapter I want to discuss with you is energy transfer. We did so far electron transfer in all these cases. So now we do energy transfer, and Okay, it's working again. So the tea is not here, so we continue a moment. So in the second part, I would like to introduce energy transfer to you, and that is complementary as the other activation mode to electron transfer. With the electron transfer, the photocatalyst will transfer an electron or take an electron from the substrate. In the energy transfer, the catalyst might transfer energy. And one, I think, very exciting application for this is what I think originally the term was coined by Jimmy Weaver. I think that's at least where I read it the first time in the paper, uphill catalysis. And the idea of this, let me just show you a diagram first before we go into this. The idea is that if you have a starting material, and if you want to go from the starting material to the product, the reaction usually works if it is exergonic, right? So the starting material is here somewhere, and then you go to a product which is lower in energy. And so, of course, there's an activation barrier, but thermodynamically, this is favored. And if you want to run an unfavored reaction thermodynamically, then typically what you need to do is you need to use high energy reagent. And one of the examples for this, which we looked in earlier, is that if you do the cyclopropionation of a furane, this would be energetically uphill if that would, if you would just look at this alone. You break the aromaticity, you make a strained ring, and so on and so on. But you counter this by having a high energy reagent, like a diazo compound, right? And so this way you essentially lift your starting materials because you have a high energy reagent, and if this extrudes nitrogen and makes the carbene, you have generated a highly reactive intermediate on a high energy level, right? And so this is what we very often do in many type of reactions. Very often we use strong bases like butyl lithium, LDA, and so on. It's always the same thing. We're making a reactive intermediate which is high in energy, and we are able to do this by specialized stoichiometric reagents. But the idea with photochemistry can be different, because with photochemistry, you might be able to simply lift your starting material to a excited state, and the excited state is much higher in energy than the ground state. And then from there, if you go to a product, everything might be thermodynamically downhill. And we might have had this also in these SET, in these photoredox reactions that we had, but we talked a lot about these ATRA reactions, right, where we have an alkene and then add a radical precursor, and we are getting something like this, right? This is probably not uphill, this is downhill. If you again if you just try to make a guess, you would say, hey, wait a minute, I'm exchanging pi bonds for sigma bonds, right? And that must be thermodynamically downhill. So all the examples I have shown you in the previous section, where of course would go through an excited state, but nevertheless, if you look at the reaction coordinate, it would still look somehow like this, where the product is lower in energy than the starting materials. But I would like, with this energy transfer, there are now a lot of examples known where you actually start from starting materials, and these starting materials are lower in energy than the product. So the reaction is endergonic, and the way you do this is that you bring in the energy in form from light. You bring in the energy, and this way you can go to a thermodynamically higher lying products. And I think that is exciting for many applications. So first of all, it's exciting for reactions you want to drive, which might be thermodynamically unfavored. But also, and I will show you some shy examples of this, it might have relevance to store sunlight in form of chemical energy, right? Because if you have a process which is thermodynamically uphill, you have essentially stored the energy you get from your light source, and ideally it would be sunlight, and you would have converted it into chemical bonds. And then if you in some reason should be able to release it again, you might have a chemical storage system. As I say, one has to be very careful, very shy, and especially things where you convert a product, a starting material, to a higher energy product. There are still many different difficulties and obstacles to use this as an energy storage form. But it's one approach you can think about. And I think the interesting or the important thing is we are pretty good already in producing renewable energy, but we are terrible in storing it. And storage is a huge problem in all kinds of ways. We do lithium batteries, and you see how well this works. We are changing every 30 minutes. It's not lithium probably, it's nickel hydride or so. We're changing the batteries a lot. But also just to store 1 kilowatt hour, I think 0.7 kilowatt hours, you need 1 kilogram of lithium, right? So really energy storage and have it in a way that you can transport it from A to B is a big issue. And that might, if we think about storing energy in form of chemicals, chemical bonds, this might be one way to think about this. And so therefore, these energy transfer can be quite useful. So you guys stop me when the tea has arrived, right? So it's not my fault. They told me I continue until the tea arrives. Okay. So if we think about energy transfer, we bring a molecule into its excited state. But in this case, other than in the photoredox chemistry, we don't transfer an electron. We have a catalyst which is in the excited state, and then might transfer the energy to a substrate. And this can also work directly on the substrate, and I think one of the best examples for this are carbonyl compounds, right? If you shine light on a carbonyl compound with the right wavelengths, then you are able to bring this in the excited state, and then the same thing like which we discussed earlier, you bring it into the first excited singlet state, and then it has to do an intersystem crossing, and then from the triplet state, you can get reactions out of this. And this triplet energy, the energy where the triplet is higher than the ground state, this is the energy you can transfer to a substrate, right? So very important, you need to know how big the gap is, the energy gap, the triplet gap is, and you need to match it with your substrate so that this reaction can work. And out from the 60s and 70s, there are quite a number of reactions known which can utilize the idea that you can use carbonyl groups, excite them, bring them into the excited state, and then do different type of reactions. And I'm going to show these to you a little bit. I'm not sure if you know them already. Also, the Norrish 1 and Norrish 2 type reactions are typical cases for carbonyl groups. But then also very important is the Paterno-Büchi reaction. It's a 2+2 cycle addition with alkenes, which can do this. And then you can also do isomerizations and photoreductions. And so again, here's another representation of this energy diagram which I showed you earlier. So we use excited states to lift up our starting materials, and then this can go both ways. It can either go to a thermodynamically less favored product, but it can also help you to start from the excited state and then overcome a very high transition state barrier, right? And the advantage is if you start from the excited state, from the activated starting materials, this might be easier than if you would start from the ground state. Okay, so the Norrish type 1 cleavage is a reaction which is depends in many cases quite useful, especially when you can do this intramolecular. And so what this is doing, let me get the oops. Okay, so doesn't matter. We have it here already. Nope. This one here, right? So what the Norrish-1 cleavages do, if you excite a carbonyl group, then the adjacent carbon-carbon bond might cleave. And what you are generating is radicals, and this might occur twice. Driving force, one of the driving forces is probably that you make a relatively stable carbon monoxide here. And then the two radicals might recombine. Something we don't see so often. We talk about transient radicals usually do not find themselves. But then if this can be done in an intramolecular scenario, this might be a very useful and good reaction. And you see an example here where you have this cyclopentanone here, and then under the irradiation you go to a cyclobutanone and carbon monoxide, right? This is exactly the reaction we have seen up here. And again, in the terms, if you think about uphill chemistry, one would have to look at carefully also at the carbonyl group, but you see you're making a more strained system. So you probably introduce the chemical, the light energy, which you have been using here, you introduce in the end in your product. This could not be really used for an energy storage system because this is not reversible any longer, right? Because the carbon monoxide is gone. But it shows you that you can make strained systems in order to do this. And then the Norris-2 type cleavage can occur if your carbonyl group has in the 1,5 position, so if I calculate my carbonyl oxygen as 1, 2, 3, 4, 5, if I have a hydrogen, then this hydrogen can get abstracted from the excited state of the carbonyl group. The best way to think about these excited states is always as a diradical. So if you go if you do the excitation, if you want to think about the chemistry which can out of this, draw it as a diradical, and then you can get chemistry out of this. And so typically what is a very good process are these 1,5 hydrogen shifts, and you can easily see why that is, right? Because it goes, if this gets transferred here to the excited state of the oxygen, it goes through a 6-member transition state. And that is very, very useful, and that typically is favored over a 5-member transition state or even larger rings, right? So these 1,5 shifts are very, very typical. And then you see that you're generating, and it's already seen here, my radical dots have been a little bit big. You can see that you're forming a new diradical, right? You have transferred the hydrogen to the oxygen, and then you have the radical center on this carbon, and you have the radical center on this carbon. And this can do now two things. It can do a radical coupling, and then again you form cyclobutanones. So again, that's probably definitely thermodynamically, if you think about this again, it's definitely thermodynamically uphill, because you're sacrificing your very stable carbon-oxygen double bond. We talked about this. And at the same time, you make a cyclobutane ring. Cyclopropane, we talked about the ring strain. I said it's about 27 kcal per mole. Cyclobutane is about the same. It's also in this range. So it's quite a strange system. And so therefore, one of the alternatives is instead of doing the cyclization, it can also undergo cleavage. If it cleaves between this carbon-carbon bond, then it would form two alkenes in this moment, and that is also a reaction pathway, which typically you have a competition between these two reaction pathways, and then your enol ultimately tautomerizes over to the acyl compound. And so these are Norris-1 and Norris-2. And I just said that the 1-5 shift is usually the one which is preferred. But if you have a situation where the 1-5 shift might come from a sterically hindered position, then also the 1-6 shift might be feasible. And this is a very interesting example shown from Axel Griesbeck, who is a very famous, well-known photochemist in Germany, and he has been able to show this example, where instead of the 1-5 shift, the 1-6 shift, which would go now through a 7-membered transition state, occurs. Again, he's making this diradical, and now there's another, that's the interesting thing. So how is this stabilizing themselves? Here we saw what it can do. It can cleave by fragmentation this bond and form these two alkenes, or it can do the radical-radical coupling. So how would it have been here? It could have probably also done the radical-radical coupling to see a 5-membered ring here. I'm not sure why this didn't happen, if that was a problem for steric reasons. And instead, it would do now a 1-4 hydrogen shift. So it would shift this hydrogen to this radical center here. And then you can see that this way you're generating a new double bond here in order to do this. So this is something you always have at least to consider. The 1-5 hydrogen shift is the most favorable one because it goes through 6-membered ring. But if it for some reason cannot do, you can observe 1-6, you can observe 1-4. And again, this is a contra-thermodynamic process. We are sacrificing a very stable carbonyl CO double bond, and what we are getting out in the end is we are getting out a CC double bond, right? So that again has probably gone 20 kcal downhill. Should I still no tea? Yeah, it's not my fault. I should have a big sign here. It's not my fault. Okay, we already talked. I had a question for this, but we already have answered this, that it is. Now tea? Okay, guys, tea break. I see some of you need it. I understand this. So let's have a small tea break. Yes, now I'm back. Okay. So, a little bit more chemistry before lunch. So, interestingly, remember how this came here? I wanted to ask, but this was this reaction, right? And I had prepared the question, why is that thermodynamically unfavorable, contra to thermodynamic? I just want to make you aware of something, right? This clearly cannot be an answer. You essentially phrase the question in a different way, because thermodynamically unfavorable, contra-thermodynamic means nothing else but being thermodynamically unfavorable, right? And so you're answering, this answer like this, you're actually repeating more or less the contents of the question. So always be aware of this, that you need to be precise, and I'm not sure how things usually work for you here. We are supposed to give a small exam here at the end of the course, and it will, Professor Zakar told me, it will be multiple choice. I have to think very hard about multiple choice questions, but you have seen I already have a few, so don't worry, it will not be very hard. But very often you have to write written answers or write schemes and things like this, and I see this very often, that the answers are imprecise in the way that they don't explain what it is, that they essentially in a different way say what was asked, but without giving an explanation, right? And so here in this, we talked about this, right? If you ask about thermodynamic, favorable or unfavorable, typically what I like always to do is I simply analyze the bonds which change. So I have a carbon with a CO double bond here, and now in the end here in the product I have a CC double bond here, and so I know the CO double bond is at least 20 kcal per mole more stable, and so that type of analysis. Okay, here's another reaction which is contra-thermodynamic, and these are the Paterno-Büchi reactions. Paterno-Büchi reactions make use out of it that you, again, excite a carbonyl group around 350, 360 nanometers, and then they can also undergo 2+2 cycloadditions. And they can do this even with aromatic systems like furane, and here you see the example for this, where you have done a 2+2 cycloaddition. And again, clearly, this is contra-thermodynamic, and I will actually show this to you in a little bit more detail in just a moment, because we have calculated this. This is about 24 kcal uphill in this reaction. And why is this? Because we are breaking the aromatic ring, aromaticity in a furane about 15 kcal. We're making a strained four-membered ring, so we're introducing ring strain. That's another 27 probably. So it's 27 plus 15 is 42. But then, of course, we're exchanging the pi bond for sigma bonds in the carbon-carbon regime. That should be up 10 kcal, but also we are converting the CO double bond to the CO single bond. So that again brings it downhill. So there are a couple of factors, and in our calculations we calculated that it's about 24 kcal uphill in this reaction. And then so here you have another one. You see, and here again it's another 2+2 cycloaddition. Again, I've written contra-thermodynamic probably for the same reasons. You still make a four-membered ring here, you dissolve the carbon-oxygen double bond. The one thing to realize here is that this is a reaction where you build a more strained ring system, but you also have strain release here, because in norbarmene, if you ever build this, you can already see how strained this is when you have a model and put this together. So these are the typical strained alkenes, and therefore these type of reactions work very well. It goes with very, very good yields. So here's my other question, which is very important to consider when you look at energy transfer processes. If these reactions are contra-thermodynamic, so starting material and then my product is higher in energy, why do they not go back? Why do they go to the product, but why don't they go the way back to the starting materials? Again, under the reaction conditions which we do, we shine light on there. Why do we stop at why does the back reaction is not taking place? Are you okay with this concept? That probably more or less applies to any type of these photo 2+2 cycloadditions. No idea? But this is really important from the conceptual point of view, right? No idea. Okay. That's a fair answer. I think it's very good to admit this and say, I don't know why. In an exam, I would now probably ask, okay, so tell me how the forward reaction works. Right? And if you go back to this and take a look at the forward reaction, how does the forward reaction work? My carbonyl group is absorbing light at around 365 nanometers. I excite it, and it does the 2+2 cycle addition. If I want to excite the product, what would I excite? The carbonyl group is gone. That's probably the best chromophore. Alkenes, we had that one table, around 250 or so. So this is the key idea here. In the products, very often, they don't absorb light any longer, or they absorb light in a much shorter UV range one. So I have in my starting material, I have something which will absorb at 365 nanometers. That's the carbonyl chromophore here. In the product, I might have at best the pi system of my enol, and this will, and then if you measure a UV, for example, you will find out that this is not absorbing at 365 any longer. If anything, it absorbs at a much lower wavelength. So keep this in mind. This is the idea why all these reactions can work. If they are thermodynamically uphill, they will not react back because the reaction pathway, the light-induced pathway, is not there any longer. If you heat this up, or if you do, I showed an example in a moment, if you do like the Lewis acid catalysis activation, you might open up the ring and reform the furane. Absolutely. So this might happen, but not under the photochemical reaction conditions. Okay, good. So here's the reaction from our lab. That's which the Patano-Büchi reaction is furane, as I showed you on the previous slide, was known. But we liked this. We wanted to look at this, and probably you see the idea. We did cyclopropanations on furanes, and then I told my co-workers we did this for a long time. Now let's do some other ring systems. And so then they came up and say, okay, we do the Patano-Büchi reaction. And I said, but this is already known. And they said, yeah, but we can do something more with this. Let's just have a quick look at this Patano-Büchi reaction. The phenyl group is on the same side like the hydrogens. Why is this? Should have put a question to this, but I didn't do this. Forgot to do this. Why is from the stereochemistry point of view, why is the phenyl group at the same side like on the same side like these hydrogens here? Anyone want to give me the keyword which you might want to mention? It's again a question of, I draw it over here because I can draw this here relatively nicely. It's again a question of a convex and a concave phase of a molecule, right? We have again two rings, two small rings, 5 or smaller, and they will have a concave phase, and then they have a convex phase. And the substituents, okay, I need to put in the oxygen here, and then the substituents will orient themselves on the convex phase. And so this is essentially, this means it's the same side like the hydrogens, right? So this is again on the convex phase. So keep that principle in mind, because that is seen, because we do so much chemistry in general on ring systems. That's a very, very important concept, and makes reactions very, very selective. This is the only diastereomer which you are observing. You're not observing the other one where the aryl group would have gone into the concave phase. Right? And so in this case, what they did then is show the mechanism on the next slide, but we are able to convert this into a cyclopropane. Right? And again, if you look at this, my gut feeling was that even this should go further uphill, because we're now making from the strained ring here, we're making maybe an even more strained ring here. But then when we did DFT calculations, we found out that we're actually going a little bit downhill. And the reason for that is probably, again, that we're making CO double bonds here. Again, that's the thermodynamic typical driving force. But what we like about this reaction, as I show you how this works in a moment, is you start with two compounds, and these are renewable resources. The furan, we talked a lot about this, such benzaldehydes come from lignin probably as well. And so we do a 2+2 photo reaction. It's 100% atom economic. It's a light reaction. It's absolutely clean. These reactions are close to quantitative. We store 24 kcal per mole into the product. And then in the second reaction, we are actually doing follow-up chemistry with these oxytans. And this was indeed not known to make these type of cyclopropanes. Let me show you how that works. Right, so the way we can activate these types of oxytanes is that we are using a Lewis acid, and you can see we can use very little of the Lewis acid. The Lewis acid is coordinating, and now it can open up the bond, and it can do it in two ways, right? If it can open up the red bond, and it can could open up the black bond. If it opens up the black bond, the system goes back to the starting materials. And that's why we think that such a chemistry might also be interesting as energy storage systems. But if it opens up the red bond here, then we would form this cation. And you see how we have chosen this. We have chosen a substituent here, which is a donor, a good donor. So we need to choose this substituent in order to open up this bond selectively. Our R group should be able to stabilize the positive charge here. And then this chemistry works very well. And then we have an enol and a cation here. And then if this enol is attacking this positive charge here, so you form the new bond between this carbon and this carbon. You form this three-membered ring, and then in the end, if you hydrolyze the acetal, so another water addition onto this side, and then hydrolysis of the red bond, you form two aldehyde compounds. And so we like this chemistry because at least it's one example where we do not need any pre-activation. Again, we talked about cyclopropanes. Usually the carbenes, we are either making from diazo compounds, or we're making them by making carbenes, for example, dichlorocarbons from chloroform. So typically all strong bases, stoichiometric bases, and here we have a entirely we have a complete light type reactions in order to do this. So let's look at a few more examples. This type of reaction is very often used in natural product synthesis, and again to make highly congested ring systems. Here's an example from my colleague Thorsten Bach from the TU Munich, and he showed that you can do this type of 2+2 cycloaddition. You see you get a 2+2 cycloaddition between these two systems, and you can do you can get such a ring system out of this. That was 2003, and probably if you would try this today again, you would maybe use a photocatalyst, which would allow you to absorb more in the visible light range. You see they had to irradiate here with hard UV, and that was because you don't have anything really which absorbs light well. The alpha beta unsaturated carbonyl compound, that is probably your chromophore which you excite, and but you need pretty short light wavelengths. So let's quickly talk about how is this energy transfer, how is the principle for doing this. And there are two types of ways this could go. There's a Förster energy mechanism, and this simply you bring your photocatalyst or your donor, you bring it into the excited state, and then it transfers the energy to the acceptor. Let me show this to you again. Transfers the energy to the acceptor, and it goes back to the ground state and is lifting up your acceptor, your substrate, for example, to the excited state. The second way you have is the so-called Dexter energy transfer. That probably always is happening in photocatalysis. And this is, again, you have your photocatalyst, your donor, you have it in the excited state, but now if it is doing a collision with the acceptor, what simply happens is that they exchange the spins. So from the acceptor, one electron is exchanged to the ground, to the lowest orbital of the donor, and the excited electron from the S1 molecule from the donor becomes the S1 molecule from the acceptor. And in order to do this, you need to be able to have the compounds have to be close to each other. So like this is shown here in this review. This is a review on energy transfer from Professor Frank Lorios, which I can highly recommend, which is really explains things and gives many, many examples in a great way. And so you see the really important thing is that these two molecules can come close so that they can exchange the spins which you need in order to exchange from your excited donor coming to an excited acceptor and do this. And so typically the model which is being used is you have the isolated molecules, they come close to each other, they have a collision complex, exchange the spins, and then they might diffuse it again, and you have done the energy transfer in this scenario. And so then if you want to do this, it's very important in order to exchange these spins, it's very important that your triplet gap matches, and if it doesn't match, it cannot do this, right? So so here this gap here needs to be similar. Let me see, do I have it? No. So this gap and this gap needs to be very close to each other in order to have that efficient energy transfer. And so you need to know about this. And the good thing about this is that, again, you find it in the literature. You find for almost any type of photocatalyst, you find tabulated the triplet energy, and so therefore you have the gap to the ground state, and you see it's different for each catalyst, and probably not surprisingly, it correlates very well with the absorption. So of course, if you need higher energy light, then you can reach an excited state which is higher in energy. And you see here the ruthenium bipi has a triplet energy of 46 kcal, but then if you go to iridium, so this here absorbs around 400. The iridium bipi, ruthenium bipi is probably 450. The iridium PPY is around 400, and then the benzophenone is 350. And you see the triplet gap is becoming bigger and bigger this way. And so therefore you need to know about this in order to choose if you have a substrate, in order to be able to efficiently match the triplet energy of your substrate. And again, a lot of that is already known in the literature with the triplet gap of your catalyst. But that also tells you that it makes a lot of sense sometimes to try, if you don't know the triplet gap of your substrate, it makes a lot of sense to try different photocatalysts to get an idea. And then maybe in some cases you use a photocatalyst which does not have the right triplet energy, and then this might be the reason it doesn't work. But in principle, the reaction would be okay. And so again, there is in this review from Frank Lorios very nicely, he lists a lot of these triplet energies from a lot of the photocatalysts, and then he also shows substrate classes, so quite a bit of them, and you can simply check, and then you can simply see, okay, I have a triplet energy in this substrate of 70 kcal, and so therefore I need to go to a catalyst which is close by or ideally identical in order to do this. So again, this makes the type of chemistry very, very predictive. And then you can sensitize different types of molecules, and one molecule which is very important, and that also very often comes to the question, should I run the reaction under oxygen or not? Oxygen itself can get sensitized, and there are many dyes which can do this. Methylene blue might be one, rose bengal, but also ruthenium bipi. Ruthenium bipi can sensitize oxygen, and what you are then getting, you bring the oxygen from the triplet state to the singlet state. And the singlet oxygen, that is a dienophile. This can do 4+2 cycloadditions. And so with dienes, it's a very common reaction, a very efficient reaction, that if you do a photoirradiation with oxygen, that you get the Diels-Alder adducts. So it's not a photochemical 4+2 cycloaddition. It's just that you bring your dienophile, which is in the ground state, is in its triplet state, you bring it into the form that it can do a concerted reaction in this, and that is the singlet state of oxygen. And so that is what the light is doing, but the cycloaddition itself is not a photoreaction, it's a normal thermal 4+2 cycloaddition. And you see that this works very, very well in this case here. So that's all, again, not that old of a publication. And these type of NO peroxides are a type of compounds which people are very interested in, because artemisinin, it's the number one anti-malaria drug, and this has exactly such an NO peroxide structure. And I guess malaria here, as you can also, I'm always nervous when I see a mosquito also here, but I think malaria in the cities is pretty well in check. But malaria in India, because you have such hot weather, is still something which you have here in this country, right? And fortunately in Germany also, it's not something we have to battle. Okay, so, and then we have shown the photochemistry on these type of systems by electron transfer, right? So the Yoon group, and again, there's a publication from Yoon, they showed that with an electron transfer catalyst, you can make the radical anions, especially if you have acceptor substituents here, make the radical anion and then do the 2+2 cycloaddition stepwise. But the Yoon group also showed that you can do this by energy transfer, and you see that the advantage this has is, if you go through the energy transfer mechanism rather than through the electron transfer, you can do this with different types of substrates. Because with the electron transfer, you needed an acceptor here, because otherwise the electron would not be able to get efficiently transferred. It would not be a good electron acceptor. Now here with the aryl groups, it is very easily excited essentially to the diradical, right? And you have the aryl group which stabilizes, here it is written, stabilizes essentially the radical species here. And so now by energy transfer, you will be simply able to do the 2+2 cycloaddition. This is of course what we have seen in the previous examples as well, like here in this example, here as well. But what the Yoon group was showing, and that's why I said here in this reaction, you have to irradiate with very high energy light. But what the Yoon group shows here is that because you're using a sensitizer, which absorbs in the visible light range, that you can go through longer wavelengths light and do the 2+2 cycloaddition sensitized, so you're not directly activating this to the diradical, but you go to the excited state of the iridium catalyst, and this will then do the energy transfer to get you the activated substrate here. And so we talked briefly about the idea to use these fluorescent light bulbs, right? I think it would have been nicer if they would have used an LED here, would absorb, where they irradiate exactly at the wavelengths of the catalyst. With these CFL lamps, you always have UV parts on there. And so it's a little bit harder to deduce what you are actually, since you have such a broad range of wavelengths there, it's a little bit harder to, analyze what is actually the activation of that molecule. And you see here they did some very impressive chemistry on this. So they did these 2+2 cycloadditions, and that works, makes these highly congested systems. Here you can see this yourself. If you're forming the one ring here, and then you form the next forming ring here. And again, photochemistry allows you to do this, right? Because the energy you need, you bring in through the light. And then on the other hand, this compound has no chromophore to take the energy. So this is why the reaction also in the sensitized way is not going back. Okay. Here's an example which I would like to show, and I hope we have the time. Something I have also prepared for the tutorial yesterday, and as I said, we're a little bit behind of what I thought we can do. This is now an enantioselective 2+2 cycloaddition, and that again comes from Thorsten Bach, who's doing a lot of asymmetric photoreaction. And here's a very exciting system. So you see, he has a photocatalyst, and so this is here the photocatalyst, which is typically doing the energy transfer. But then the photocatalyst is attached to this chiral unit here, and this chiral unit is an amide, and so it can recognize other amides. You see, by complementary forming hydrogen bonds, it can recognize a substrate. And so he was using this substrate with this catalyst, and you see this substrate has an amide, and it can get recognized and coordinated here. And so then he's ideally pre-organizing the photocatalyst with the substrate. And so the energy transfer comes from the photocatalyst to the aromatic system here in order to excite this. But the important thing is it gets only excited when it binds to the catalyst, because only then it is close enough to do the energy transfer. And so then when you have the energy transfer, then you are able, from the excited state, to do the 2+2 cycloaddition. And if you look at this, if you look at this system here, you can probably easily understand that this double bond would come from below and not from the top, because on the top your photocatalyst is in the way. And so the Bach group could show that you can do enantioselective, and you see fantastic enantioselectivity to highly strained ring systems to make such kinds of compounds. And the other thing which is quite important in these type of reactions is, we already said that it is very important that you match the triplet energy of your catalyst, and that the triplet energy needs to be at least as much as your energy gap. And one thing to realize is that you might be able to change the triplet gap of your substrate. And the way you might be able to change it is that you, by Lewis acid coordination, you can lower this. The same thing like Lewis acid is lowering the LUMO, you have the same thing, right? You have the HOMO-LUMO, this is your gap. If you bring in a Lewis acid, you might lower the LUMO. And so the triplet energy can change. And again, the Jung group here showed and measured this, that this is happening. So this substrate had a triplet gap of 54 kcal per mole, but if they coordinate this with scandium, with a Lewis acid rare earth metal catalyst, then the triplet energy drops to 33. So quite a lot, 20 kcal. And this allows you now to do the sensitized reaction with a ruthenium, in this case with a ruthenium photocatalyst. And he is using this for 2+2 cycloaddition with this diene, and you see you're forming one new cyclobutene here, between this double bond here and this double bond. So this gets excited, this makes this double bond reactive, and then 2+2 cycloaddition with the ground state of this diene is happening. And so the one thing which is important to understand is that through the coordination of the Lewis acid, you might make your system more reactive, and because you make the triplet gap smaller. But the other important realization is that in this scenario, because you're choosing a photocatalyst where the triplet energy is not sufficient to overbridge these 54 kcal per mole, what is important to understand is that this molecule alone, without being coordinated to the Lewis acid, will not react. Right? It could be, in principle, if the triplet energy would be higher than these 54, then we could also have a reaction that this cyclization between these two molecules would occur in the absence of a scandium catalyst. But the way very cleverly chosen is that your triplet energy of the catalyst is only sufficient when the Lewis acid is coordinating to this. And that way, and that's what the Jung group did, they have one of these chiral bisoxazolene ligands. And with the bisoxazolene ligand, so these is, I think we have seen some of these ligands before. All right, so these bisoxazolene, here's a pibox ligand, so this has a pyridine in between. So these are these type of chiral ligands. And he is using a T-butyl group here, so it is this type of ligand structure which he has. And so then with the scandium triflate, you're going through you're forming such a complex. And so again, please understand that this is not the photocatalyst here, right? Your photocatalyst is the ruthenium catalyst, but you do the photocatalysis in the presence of a chiral Lewis acid, and the reaction only works when the Lewis acid coordinates to the substrates, because only then you can overcome the triplet gap of the substrate, which in terms what the catalyst is offering. And you can see this is, again, I think, a very spectacular result, that he gets good yields, but fantastic enantioselectivity. Okay, I must have duplicated the slide twice. Okay, here's another thing which I really like in this concept of uphill catalysis. It's a different type of idea, and in order to introduce this chemistry I want to show you, I would like to ask you, what is the smallest cycloalkene which can tolerate a trans double bond? Right? We all know normally cyclic alkenes like cyclopentene, cyclohexene, the double bond is cis. If you want to have the double bond is trans, how big must the ring be at a minimum that that compound is stable? And I have a spelling mistake there. It should be cycloheptene, not heptene. Okay. So you guys, very good, try to decide if it should be an 8-membered or a 9-membered ring, and definitely it's not a 6-membered ring. That would be much too strange. So indeed, it's a trans cyclooctene, which most of the majority of you guys have suggested here. And so with this said, there is something pretty exciting you can do. And also I talked to one of the, not sure if I see him here in a moment, about one of your projects where you would be trying to isomerize a trans double bond to a cis double bond in order to get a cyclization. The reaction I would like to introduce to you here, this is from Jimmy Weaver, and I think in this context, he used this term uphill catalysis, where he's doing the opposite. He is taking a small ring, you can see here, this is a 7-membered ring, so that would normally not be stable, a trans-alkene you cannot form in this. But what he's doing is he's irradiating it. And so in this way, it starts, if you are irradiating alkenes, you will get a equilibrium of the cis and the trans-alkene, right? And the reason this probably works is you go through the excited state, you can again draw this like as a biradical, and in this excited state you have dissolved the double bond, so you can rotate around the single bond, and so you can get cis-trans isomers, and you see what I asked. And so the exciting thing about this is that if you would have what he is doing here, if you would have if you would have such a cycloheptene here, that is usually would not be very reactive for, and certainly not for a thermal process, right? If you have a 2+2 cycloaddition, we all know that this will only works photochemically, but it will not work thermally. But what he's doing here is he is irradiating this with an energy transfer catalyst. So clearly this has not the can irradiate this in the visible light. And then what he's doing is he's isomerizing in an equilibrium the cis-alkene to the trans-alkene. And in the trans-alkene, he's inducing, of course, incredibly strain. In this cycloheptene, it is calculated that this should have 36 kcal strain energy, so that's much higher than a cyclopropane would have it. And because of this now, it suddenly is doing a 2+2 dimerization with one of the cis-alkenes. And the reason he could find out that this is not a 2+2 cycloaddition is because the stereochemistry here is in a way that it has to come, that one of them has to come through the trans-alkene here. And of course, it's not a concerted reaction any longer, it's probably stepwise, because the 2+2 thermal reaction is not allowed by the Woodward-Hoffmann rules. But here it goes probably through a diradical type mechanism, goes stepwise, and the reactions are very efficient and can occur. And he showed later on that this type of chemistry can not only done for 2+2 dimerizations, but you can have, for example, a diene present and then get Diels-Alder reaction going, which would under thermal conditions not work because the homo-lumo difference would be too big. By introducing strain into the molecule photochemically, then the reactions suddenly start to work because the strain release is really the driving force. And here's another example what the photochemistry can do. And again, I think this is very exciting. This is work from the group of Frank Glorious, who showed that the energy transfer conditions actually allow you to de-aromatize arenes, and the one which he's using are these isoquinolines. Isoquinolines are not quite as aromatic as benzene would be or as naphthalene would be, and he could show that under the energy transfer conditions with the right iridium photocatalyst, you go through such a diradical, and then this diradical can actually do. Again, it's a formal 4+2 cycloaddition, which occurs now, but it's not a concerted one, right? It's essentially a radical type mechanism where he is then combining the diradical with the alkene. And so this way he's able to do de-aromatizations of very simple flat molecules. This type of chemistry is often coined escape from flatland, right? You have flat aromatic systems, and now you make 3D scaffolds. And that is indeed, again, very nicely and very easily done and could not be really done by any type of other methodology. I can also show you that typically in the de-aromatization, or typically in this uphill type catalysis, there are also single electron transfer processes, of course possible. And that is an example here from our group where we photocatalysis, but this time again by photoredox catalysis, we are making the radical here, which I have shown you previously already a lot, by the oxidation of the malonate. And the way we have designed the system is that if this reacts with an alkyne, show you the mechanism on the next slide. If this radical reacts with an alkyne, we are having these vinyl radicals, and the vinyl radicals indeed are able to do a de-aromatization here, and because the vinyl radicals are very unstable and very reactive, they go into the arene and will ultimately do the de-aromatization of this type of system, right? And so the photocatalyst in this case helps us to make these highly reactive radicals, which then get relayed further with the reaction of an alkyne and then ultimately the de-aromatization. The one thing which I think is always careful, where you have to be careful, is again, we thought that this is maybe something which is thermodynamically uphill, and if you consider usually, how do I convert a benzene? How do I convert this to a cyclohexadiene? You see, this is ultimately what we are doing. How do we do this normally? What is the reaction? Which one? Say again. It's a Birch reduction, right? So the Birch reduction uses lithium and ammonia. So again, high energy reagents in order to do the reduction. And here, of course, in a different setting, because we're making a spiral cycle, but we're making the same type of cyclohexadiene as a product. The one thing to be careful about this is always like how uphill or downhill is this, and at least for our reaction, we calculated here that it's probably not, it's relatively thermoneutral, because don't overestimate the aromatization stability. We cracked the aromatic ring system here, so we're going, we overcoming the aromatic stabilization, that is 35 kcal, but then at the same time we're making sigma bonds at the expense of a triple bond, right? And so when we calculated this, it was more or less thermodynamically the same way, the same thing, but from the transition state, from the activation here, the de-aromatization, of course, had a very high barrier, and that is something which we were able to overcome by generating photochemically a radical and then going through a radical pathway which has a lower barrier than the closed shell pathway would have had to go to the products. Okay, so this is what I wanted to briefly tell you about energy transfer. Now I need to think about, because we started, Sangeeta, help me, we are doing until when? Until 1:15, right? Okay, so there are essentially, there are two things I can do. I think I still have a few questions from this tutorial, but I think maybe very quickly. I wanted to go over one thing which I felt is important. Wanted to go with you, and before we start on something new. Because I think in all these scenarios it is important to always think about, when we think about any type of photoredox catalysis, how do we close the cycle? And this might be very different even for the same reactions. And for this, I wanted to give you an example. We talked about this already, and I think we have drawn this, and so I'm not going to ask this again. Oh, you already answered this. It was interesting because I had it in the other presentation, and then it is doing the same thing. So here's another reaction, which we did in our group. And let me see. Yeah. And so this is a reaction which takes a carboxylic acid, and then it decarboxylates the carboxylic acid. And then we are in the same scenario which we had before. I told you that when you do this with copper, so you see you go from copper 2, and then it's doing a dissociation, a homolysis, goes to copper 1. It makes the carboxyl radical. The carboxyl radical loses carbon dioxide. And so as the first intermediate, you get this radical, and this radical traps oxygen very efficiently. So you get this, and then, so since you have copper 1 here now, your copper 1 will coordinate with this peroxyl radical, and you see in this way it becomes copper 2 again. And if this is now, so let me just, so that it becomes clear, let me just put an X here so that we can easier see what the oxidation state is. And if this is now eliminating the hydroxide here, you are forming the carbonyl group, which is the carbonyl compound, which is now has lost one CO2, and you're regenerating copper 2, right? Because it has eliminated copper 2 hydroxide. So that's why I think it's okay, right? The catalytic cycle is closed, everything is fine. There was a very interesting paper from the Gian group again, 2 years ago, 3 years ago, came out in Nature Chemistry, and see what they did. They are taking also copper 2. They also do a decarboxylation, but they do this in the presence of a nucleophile. So the sulfonamide is the nucleophile here, and then they get, you see, they get the truncated. I gave you an R group too many here. I was a little bit too fast here, so this should be gone. So they get the truncated one, which they couple here with the nucleophile. And you can see what they do is they do the whole chemistry in a glove box under nitrogen atmosphere, because they need to be absolutely sure if you have oxygen presence, once you form the decarboxylated radical, if you have oxygen present, it really traps it immediately. So they needed to do this in a glove box, and then this way they could get the coupling between the radical they are forming and the nucleophile. So here's my question. How is the catalytic cycle closed? If you think about this, if you go through this reaction, how do you close the catalytic cycle? Or how does this work? Just go out, because I think I will want to have a new page here in just a moment. Yes. Because we need to think about the mechanism, and for this we need a new page. So do we have any answers? I show you the reaction again. You see, you start with this. Let's already start on the reaction mechanism. So they start with copper 2. They do the decarboxylation. They oxidize the carboxylate. and this gives you copper 1. Then they decarboxylate it. This gives you the radical, and then they trap it with a nucleophile. In this case, the nucleophile here has a proton on this, which is lost in the end, so you get, and then they get the coupling between the R group and the nucleophile. We are still at copper 1. Sorry?
There is another hydrogen on the nitrogen.
Yeah. But, okay, let's see here. So here, like, right, you have the NH2, but that is lost probably as a proton. But that's the interesting thing, right? So how does this coupling work? It's not getting lost as a, do you think the proton could somehow become a hydrogen atom, or the hydrogen atom could become a hydride in order to oxidize? So you have the proton, and the copper 1 is getting oxidized and is reducing the proton to an H atom or H minus. I haven't really seen this. Sorry?
Cation.
Yeah. How do you do this? So I have my radical, I have the nucleophile. So you said something about a cation. So how do you get the cation? If you want to go from here, it's a good idea. So Sangeeta has a good idea. If you want to go from the radical to the cation, what do you need to do? Is that you're losing an electron, right? So the copper 1 will become copper 0 because you need to give the electron to somewhere. You're not doing this, right? If you want to be, you see, this is the point. If you want to be catalytic, and you have copper 1 here, and you want to go back to copper 2, you would have to make the anion here. You would not have to go to the cation, but you need the cation because the cation now will recombine with the nucleophile and make this and the H plus, right? That would be the formal way. So you would need a, but then if you go from here to here, this is a oxidation. So you need an oxidant. But in order to go back from copper 1 to copper 2, you need the opposite. So I see nobody knows. It's probably a good thing that he knows, because the catalytic cycle is not being closed. Yoon used in his paper 2.5 equivalents. That is not a stoichiometric reaction any longer, not a catalytic reaction any longer. It's a stoichiometric reaction. And so because he needs more copper 2 to oxidize this radical to the cation and then do the coupling. And Yoon points out, I think he had in a way a good point here. He says, you know, copper is inexpensive. It is acceptable to use copper 2 as a stoichiometric oxidant. And so that's how he claimed it. And you see, the thing is, we tried something like this as well, but we tried to use oxygen as a stoichiometric oxygen, but we always trapped the radical with the oxygen rather than getting catalytic the copper 2 again and then use this in the next step to reduce, to oxidize the radical. And so this was Yoon's first paper, and then he subsequently showed, he did the right move. What would you do if you have read this paper? You would say, okay, copper 2 might be an inexpensive stoichiometric oxygen, but even more inexpensive would be probably iron 3, right? And so he did the same chemistry again very nicely and showed that you can also use iron 3 in this. But again, very importantly, stoichiometrically. You're not able to close the cycle. Okay, so this was one case, and interesting, Wacker process. You need to think about this. In the Wacker process, you're absolutely right. That is a palladium-2 process where the palladium becomes palladium-0. You need to reoxidize the palladium-0. You use copper-1 for this, and then ultimately use oxygen as a terminal oxidant, right? And you're absolutely right. That worked in the ionic reaction, but the problem with the oxygen here is that these radicals, if you have a radical and oxygen, they typically get very efficiently trapped. And so that's why this, in a Wacker reaction, it works because you don't have radicals, so that the oxygen can reoxidize your copper 1 to copper 2, and then in turn the copper 2 can oxidize the palladium 0 back to palladium 2. In the ionic regime that works. In the radical regime, you have the problem that oxygen is itself a radical. Again, it's a persistent radical, and it will trap transient radicals very efficiently. And so you can see how Yun had to use that to avoid this, that he carried out that chemistry in a glove box. Okay. Want to show you again, want to discuss with you again another way, closing catalytic cycles. So here's both of the reactions you have seen, but we have not really went a lot into the mechanism. And I guess, wait a minute, I have a free page here now. Okay, very good. And you see, it's in both cases, it's one of these Giese reactions where you form a radical. Ultimately, you have this moiety, but ultimately the reaction is that you form a radical, and this radical will add to an electron withdrawing alkene, and you form the new radical, and then ultimately somehow the end product is having a hydrogen here on this. So you see, it's both times, it's the same reaction, but in the one case, it's started by a hydrogen abstraction from a chlorine radical, which we get from iron 3 chloride. And in this case, it's a photoredox process. This is this Okada technology. We discussed this, where an electron gets injected into the phthalimide moiety, and then ultimately this is fragmenting, making the adamantal radical here, and then the adamantal radical is trapping the alkene. And you can see that there are different things which are being used. So in this Okada scenario, he's using this. We have been using essentially the iron 2 chloride, and I told you in principle the radical which we are forming, if the radical gets reduced to the carbanion, in principle iron 2 could have reduced it, and then this way getting iron 3, and that would have closed the catalytic cycle. But in order to do this, you remember we had this anthracene as a mediator in between in this. But this would have closed the catalytic cycle. How is the catalytic cycle closed here in the top reaction? Because ultimately you need somehow also to get the same type of product, right? So here is the hydrogen which ends up in the product. And you go from ruthenium 2, this is ruthenium 2, you go to ruthenium 3, and this is the electron you inject here into the system. So now you need to bring back the ruthenium 3 back to the ruthenium 2. How do you do this? You cannot do it like this here, right? Here the iron 2 is getting oxidized. But here we have an initial oxidation, ruthenium 2 to ruthenium 3 to get us the electron. So now somehow we need to have a reduction in order to bring it back to the ruthenium 2. So how does it work here? Does anyone see what is happening here? The interesting thing is it must be to have to do something with this reagent here, which allows you to do a hydrogen transfer and then subsequently will be able to reduce the ruthenium 3 back to the ruthenium 2. Right? And so importantly to understand here, in the one case we need an oxidation to bring back our photocatalyst, because we have done this by the action of iron 3 chloride goes to iron 2 chloride. So we have an initial reduction, and so we need a final oxidation in order to go back. And here we have an initial oxidation of the ruthenium 2, and we need a final reduction to bring it back. And so in our scenario here, the proton or the hydrogen comes, the proton can protonate the anion if this is being formed through the oxidation of the iron 2. But the same thing cannot happen here in the top case. And so this is the question would be, how do you do this? Do you see how that works? Let me go back here. So we have this is the radical which we have. And then we have ruthenium 3, which we want to bring back, right, to ruthenium 2. But now you see we have these type of as a hydrogen donor. And if this acts as a hydrogen donor, then we get the product. That's good. We still have only our the ruthenium 3, but we are getting this type of radical. And this type of radical really would like to get oxidized. Because if this gets oxidized, you can see that I can draw a resonance structure which could give me the pyridine ring here. And so in this moment, if I have ruthenium 3, I need to do an oxidation, and this will allow me to go back to ruthenium 2. So that's an interesting technique that you can do overall a hydrogen transfer in both scenarios, where you need to reoxidize your metal catalyst or where you need to do a reduction of your metal catalyst. And this idea, and this is why these Hunch esters are these dihydropyridines are very complementary, because once they transfer the hydrogen, they actually want to get oxidized, so this radical is acting as a reductant, while in the other scenario, the reduced metal is able to reduce the radical and undergo the oxidation, and then it's not a hydrogen transfer, it's a proton transfer ultimately onto this anion.
This will be a stoichiometric amount.
Bitte? This one?
Yes.
It's stoichiometric, yes. You need a stoichiometric, of course, you need a stoichiometric reductant or oxidant here in this case. There's no way around this. As we had it in all the type of reactions, right? We always use in the end a stoichiometric terminal oxidant. This can be oxygen, this can be something else, but you need, of course, a terminal. You need somewhere needs the electrons also need to come from, right? If you do, because this is, of course, also stoichiometric, right? So you need, of course, you need, in this case, you need it. You see, in our case, in the second case here, okay, here you can argue you need a stoichiometric proton. But you're right. So that is indeed you need here the stoichiometric, ultimately stoichiometric hydrogen atom transfer reagent, which then also can work as a reductant to close the stoichiometric cycle. Okay, so again, complementarity, but always careful, always think about what is happening with your metal catalyst, how is it changing oxidation states, and how can you go back? Okay, let's, I wanted to talk a little bit about asymmetric catalysis, but I think I will leave this out because we are running behind. And the one thing I would like to discuss with you, and don't worry, this will be not complicated, but it's a very emerging technology in the moment. I don't know, did anyone run an electrochemical reaction in your lab? Did you do this? Anyone? No. So this is something in the moment which I think is emerging quite a bit. And when we talked about this, we had one question earlier, somebody wrote to you, it has become easier to do it, and it's exactly right. It's, you can buy ready-made electrochemical cells. Typically, such a setup costs about 3,000 euros. That's 300,000 rupees, right? So in this range. And then you have essentially everything is ready. You have your cell, your reactors, the electrodes, and then you can start doing the electrochemistry quite well yourself. It's quite readily without this. It's also relatively easy to build it. We use sometimes graphite electrodes, so that if you buy for pencils, if you buy graphite mines, you can use them as electrodes. It's then more expensive if you have like platinum or also electrodes, but in many cases these carbon electrodes, and then you can buy them for much money from Aldrich, or you can buy them from the pencil store for nothing. They work pretty nicely, and then you have to just put on clamps on this, and then you have your chemical cell. And the reason that becomes in the moment so popular, I believe, is also because photocatalysis became so popular. And think about this, in the photoredox catalysis, we are shuffling electrons back and forth, right? So we're giving an electron to a substrate, we're taking an electron to a substrate. And this, in principle, you can also do by electrochemistry. So you can get an electron from your electrode, or you can take an electron from the electrode. So that is an interesting approach. And in addition, we talk a lot about closing electrocyclic cycles, but that closure can come because you have an electrode as a reservoir of electrons, or as a reservoir to take away electrons. So you might not have the same problems of the catalytic cycle because you have essentially excess electrons or holes available. And I think this is what makes this electrochemistry really quite popular in the moment. And so I have given you here just from a tutorial review. This is a really fantastic perspective here, new trends in electrocatalysis, where you can read more about about electrochemistry, and they explain this a lot. But in principle, you have your electrochemical cell, and this can be a divided cell, as I've shown it here, where you have a cathode and anode in two different areas, and you just connect them by a salt bridge so that you can have the charge flow. Or you can have it also in the same pot, a so-called undivided cell, and do the chemistry there. And again, it works in a related way to photocatalysis, but it's a little bit different in this way that you can, and it's the most of the reactions, and probably the only reactions, because otherwise you're running out of time, is I will show you which will take place on the anode. And so the anode, if you do a reaction on the anode, you do an oxidation. And so essentially what you do is you have your substrate. Let's take, because we will see this in a moment, let's take a halide, I2, and if you oxidize this, you might get 2I plus, right? So you might be able to do an oxidation on the anion, anode. And so in order to do this is you need to take away 2 electrons. And then these 2 electrons have to go somewhere. And that is why most of the reactions you see in this scenario, because then on the cathode, simply an acid might be your electron acceptor. And so on the cation, typically, what happens is that you generate hydrogen all the time. And so this is essentially now your catalytic cycle, right? You take away 2 electrons here from your substrate, and you carry the 2 electrons to the cathode, and there you need to get rid of them any longer. But if you have an acid present, you just reduce hydrogen. You just reduce the proton and make hydrogen. And so this is a scenario which works quite nicely, and most of the applications indeed go with this, that you start with an oxidation on the anode, and in principle you could also start reactions at the reduction of on the cathode, but this is not as often seen. And so again, there's a second review. Also, you see this all pretty new reviews where people simply show what you can already do. And so that we just understand this, let me just show you a few examples. And so here's an example which, if you analyze this, you have a styrene here, and you have your nucleophile. You have a nucleophile here with this, and then you do this reaction in methanol. And you see what you're doing in the end. You're essentially doing an amino alkoxylation of your alkene. Right? And if you would do this, think about this in an ionic way, think about this, what you would do. If this would be the nucleophile, if this would attack here, this electron pair would go out, you would have a negative charge. If you want to bring in this now, what will you need? What would be the synton you need? If you think about this, so you have a nucleophile, the nucleophile attacks the double bond, you would have the negative charge here. If you want to get a product like this, what would you need? You would need O-methyl plus, right? You could not use, normally methanol is a nucleophile itself. So what you do here is you bring essentially 2 nucleophiles to the double bond. So somehow you need to take away electrons, because that otherwise it would not work. You see, as I say, you would formally need an O-methyl plus. So you would go from methoxide MEO minus to MEO plus. That's of course not really possible. But the way this is being done here is that they use as a mediator, they use iodide, right? And so here is the reagent which you can oxidize, right? And so they oxidize essentially the iodide in this case. In this case, they make iodine. So again, this is an oxidation. and this takes place on the anode. So it's an oxidation because you take away 2 electrons. And now the iodine can essentially react, as we know it, from electrophilic brominations of double bonds, right? It can react as an I plus a I minus type system. And so what it does here is it is forming this iodonium ion. And now this is like what the I plus is doing. You all remember the reaction of a bromination of an alkene, right? There you go through the bromonium ion, and then bromide is adding, and you form the dibromo compound. With iodine, you usually never form diiodide products because the carbon-iodine bond is too weak. And so that is thermodynamically not favored. So the I plus as an electrophile will activate this, but then normally you need a different type of a nucleophile in order to, the iodide then will not attack it because you have dissolved the CC pi bond, but you have made 2 very weak carbon-iodine bonds, and that's not possible. But in this case here, we have a much better nucleophile available, and so we are able to do this. And so we are able to do the first ring closure here. And then in this case, you can terminate the reaction by displacing this methanol, displacing the iodide, which then will give you the product, right? And so what you have done essentially, formally, you have taken away, you have taken one iodide. I have produced it here like this. Iodine, 2 iodides give iodine, but you could also think about this as a redox cycle that you say, I start with iodide and I generate I plus by taking away 2 electrons. And this is formally the same thing. When we thought about hypothetically this reaction, this is the same thing like going from methoxide to something like methoxide plus, but that is of course much harder to do because the iodide to oxidize is easy, the methoxide to oxidize is very difficult. And so this is why you need the mediator in there. If you don't have the iodide in there, you could think also, why isn't it working also without the mediator? Because my electrode could oxidize the methoxide. You need much higher current in order to do this. And so the iodide has become really popular, again, essentially to act as a shuttle. And also please note that it's catalytic. They have a pretty impressive catalytic amount here with 50 mole %, but it's overall catalytic because you see here this final nucleophilic substitution, I am regenerating, I'm throwing out iodide, and this iodide then of course can get oxidized again. So it's catalytic, and this takes place on the anode. On the cathode reaction, because somewhere we need to get rid of these 2 electrons which we have been stolen, the iodide. On the cathode, probably again we have a protic solvent, we have methanol, and the methanol, 2 methanols take the electron here and will form hydrogen plus probably something like 2 methoxides, right? And so that is what counterbalancing this type of chemistry. And so I think that's a pretty good and good to understand example. And there are a number of more examples what you can do. You see here it's the same idea in this type of substrate. What they what they do is, in this case, you oxidize a carbanion, because you see that hydrogen is next to an electron withdrawing group, and so you can very easily take this away. So you make the anion, and we have seen in the photocatalytic reactions that you can oxidize these type of anions by photochemistry to make radicals, right? And in the same way, you can also make the anion here, but then again, if you make again iodine plus from iodide, so again the same idea, iodide goes to iodine plus. If you after the deprotonation form an anion, this anion in the first step, so in the first step you would have your anion, and this anion can combine with the I plus, to give you to do this type of iodination, right? In the previous example, we would add the I plus to a double bond. Here we're adding the I plus to a carbanion. And then if under the basic conditions, if we would deprotonate here again, then we're getting the anion here, but this is not the electrochemical step any longer. The electrochemical step is the iodination in alpha position to the electron withdrawing group. But then once you have the iodide here, if you do then the deprotonation again, and then you can see what can happen, you can eliminate now in the 1,3 elimination the iodide and form cyclic systems, and you see a few here. You can form cyclopropanes, you can also form cyclobutanes. It all depends how your tether is being chosen. And again, I think this is pretty exciting, because in principle this should be again catalytic in iodide, because what you do here, of course, is you generate I plus, but then the I plus combines with the cation, and then you throw out in this elimination reaction. In the end, you throw out the iodide, and then you have essentially regenerated, right? You can see that it is more or less catalytic, still relatively high amounts, but it's of course sodium iodide is of course not very expensive, and you see here in some cases they even take one equivalent of the sodium iodide. But again, in principle, it should be a catalytic process. And very nicely, overall, look what you have accomplished. You have made these small rings, cyclopropanes, cyclobutanes, by a twofold CH activation in a catalytic manner. So I think that's, again, shows you the power this type of chemistry might have. And here's another pretty exciting way to do an electrochemical reaction. See, these authors here have accomplished a difluorination of an alkene. So dibromination, trivial, right? We take the alkene and bromine. Dichlorination, also relatively trivial. In principle, chlorine, or I showed you the chlorine radicals you can get from iron 3 chloride or so, and then you can do a chlorination as well. Fluorination, not so easy. I don't think that how would you do it? If you would do it analogously to a bromination, you would have to have fluorine gas, right? I think there are only 2 or 3 labs in the world who are able to handle fluorine gas. I'm not sure anybody in indoor can do this. Probably not. No one in Regensburg can do it. You need special everything in order to, because it's so corrosive, it hits everything, and it hits also glass, because the moment it makes HF, then it's also it eats the glass, but it also reacts with steel and everything. I think everything needs to be Teflon in order to do this. So very, very difficult. So essentially, I think 3 labs or so in the world are able to handle elemental fluorine. But see how nice, how that is accomplished here. So they accomplish a difluorination. So essentially, they are able to add the fluorine, add formally the fluorine to to a double bond. But what they do, the same principle which we have seen before with the 2 nucleophiles. You see, this is just it's in a way a variation, but also a very clever variation, right? So here, in this example, we have also added 2 nucleophiles to the double bond, and we have taken the 2 electrons mediated by the iodine away so that 2 nucleophiles would go to the double bond. And this is something they do here as well. They add, essentially, they don't add fluorine, they add twice fluorides, and then the electrochemistry takes care of the 2 electrons which you need to get rid of, right? And the way they do this here, again, also very nicely, they're not using iodine here, they're using iodotolerine. What am I? Yeah, okay. So they're using 4-iodotolerine. And now if you oxidize this, so ultimately what we want to do is we want to take away 2 electrons, right? And then 2 electrons and let me just put it like this. I can talk about if this is the best way, but if you take away 2 electrons, you could accommodate the 2 fluorines here, right? Because this is essentially, we have 2 F minus, we take away 2 electrons, and then we could have such an iodine 3 process. It's probably stepwise, right? It's just 1 electron is taken away, 1 fluoride might add, and then a second electron is taken away. So probably you go through something like, this, and then the alkene might attack this, and so you form such an, as it's shown here, you form such an iodonium ion again. And if this gets attacked by the fluorine twice, you end up here. So you see the first fluorine attacks here, and then you still have the aryl fluorinated compound like this. And if a second fluoride is displacing this, then you go back to then you have accomplished the difluorinated compound. And so again, if you think about this, there are very few alternatives, if any alternatives, to achieve this type of transformation. And I think this is really a fantastic example which shows you what you might be able to do. Let me see, we have not too much time left. Let me see what I wanted to show you here. Okay, maybe as one example, I show this to you here still. Look at this. They have here a alpha alkoxy ether here, and then in the end, what they are able to do is they add 2 equivalents of methanol, get added here, but then ultimately what is happening is that this bond here is being cleaved to make an aldehyde here and get rid of this phenolic group here. And again, it's the same idea. So the iodine is able to make iodine plus, And with the iodine plus, is possible to do it in the same way like we looked at this before, is doing an iodination on this molecule here, on this carbon. And at the same time, the methoxy group, if you have methanolate here, might add to the carbonyl group. And then what you do ultimately is you do an epoxidation because you throw out the iodide from your alkoxy group here. And so if this gets hydrolyzed, let me see if I see this correctly. You see now here on the oxidation state of an acetal. So if this gets hydrolyzed by water, then you're cleaving off this group and you make the carbonyl group here. And this is actually an interesting reaction because I'm not sure if you realize that this is the one structural element. It's the one structural element from lignin. And so this might be an electrochemical way to cleave lignin into smaller parts. And that is what is being shown here. I thought, wait a minute, where is the... I'm sorry, I think I'm missing one slide here where I had the mechanism on this written up a little bit more, in a little bit better way. Right, let me just point out here what we are doing. Or since we do this in methanol, I think I should have drawn this in the other way. I'm sorry. So if I let the methanol attack here on the benzylic position, and then we open up this one here, you see then I'm getting the ketal. And another ketal here. You see if this gets protonated, then I have the semi-acetal here. If this gets hydrolyzed, I'm getting the carbonyl group here, right? And the initial iodine oxidation, of course, goes through you have an attack on the H+, which attacks the I+ attacks the enol, right? That's how that initial intermediate is being formed. And so again, this would be catalytic in iodine, and it would cleave this very important intermediate in lignin to make ultimately such an aldehyde, and the other component which you are getting out of this here is phenol. Okay, so let me see. I have given you a number of more examples where you can also, we have done iodine the whole time. There are also quite a lot of other types of oxidations you can do. You can generate nitrate radicals by oxidizing nitrite. So you see, it's always the same idea. You somewhere make an anion, and this anion you do in one electron oxidation. And so people have been utilizing these NO3 radicals quite a bit. We are running out of time here. Let me see. I give you a lot of ideas here, a lot of examples. One of the ideas, probably again in the context of photocatalysis, we have talked so often that we need to readjust the oxidation state. In order to catalyze a photocatalytic cycle, we need to bring back our metal to the original oxidation state. And there also electrochemistry can play a very important role, because if you end up with the wrong oxidation state in your catalytic cycle, then electrochemistry might be able to bring it back, right? So and that is something. Let's see if we have a few examples here. I want to show you exactly, especially this one where you reoxidize the wrong oxidation state. So we have seen a lot of reactions where we have brought copper 2 to copper 1 and then wanted to get copper 2 back. Here was an example where they have manganese 3, but then it ends up as manganese 2 because, again, you see, very similar to what we have discussed before. So you have manganese 3 azide, and I showed you that we can do azide radicals with copper, but you can also do it with manganese. And then you have manganese 2, the reduced version, and the azide radical. And now it's the question, how do I bring back the manganese 2 to the manganese 3? That's what we discussed in the photochemical regime, and we needed oxygen, if you remember this, to bring this back. Here they just need the electron anode, and they reoxidize the manganese 2 by the electrode back to the manganese 3. And again, this electron, which they take away from the manganese 2 here, is being used here on the cathode to complete the reaction by simply reducing a proton here on the cathode. And so this is also a very good way. You see where the examples I showed you, we were struggling in the photochemistry a lot with this idea of readjusting the oxidation state of a metal ion, and that is something photochemistry can do, electrochemistry can do. And so here in this case, apparently this azide radical formation went by itself, but also one of the variants people do a lot is they do photoelectrochemistry. So in our case, and we want to try this at some point, we had the copper 2 azide complexes, and we needed light in order to go to the copper 1 and the azide radical. And there's nothing wrong with this, that you can do electrochemistry and at the same time irradiate your electrochemical cell. So you can do the combination of photo and electrochemistry. And I think that is also a very upcoming area, and we will see this, I think, in the future quite a bit more. And so people already do this also, like I just said, copper 2 to copper 1, or so you can do the reoxidation of iron 2 to iron 3. And I show you some examples. You see I have here oxidation states which are difficult to obtain under other conditions, where you make, for example, here a copper 3 intermediate, because the nice thing is, what limits the potential you can use in an electrochemical reaction? How strong can you apply an electro potential? How strong can you go? You see, with the photocatalyst, we were limited what the photocatalyst can do itself. How strong is the reduction or oxidation power of the photocatalyst in the excited state? With the electrochemistry, you can essentially put on you don't need a photocatalyst which has a given oxidation or reduction potential. You can just increase the current, right, and make it stronger and stronger. And so typically, how strong can you go? What is your limitation? So you have a substrate which you would like to oxidize, and you just say, okay, I'm cranking up the voltage until it is willing to oxidize. And your limitation is the solvent you do the reaction in there, right? If you start oxidizing the solvent, then you will preferentially oxidize the solvent and not your starting material any longer. And so that is what where you need to be what you need to be aware of. You need a solvent which is still dissolving your organic compounds, but you cannot apply a potential for oxidation of your substrate if it would oxidize already your solvent. And you see here typically quite good solvents are solvents like DMF, or very often water or so, where you can go quite high with the potential before you start running into a problem here. Okay, so I think at this point I stop. I This just was meant to be a short introduction into organoelectrochemistry, but I think that's something you should keep your eyes open, maybe also discuss in your groups. Should we have the possibility to apply it, to have also such technology available? It's not very expensive. As I say, in the easiest way, you build it yourself. It's very often more the barrier. I had the same thing. We bought one of these electrochemical kits, but because there was one student who wanted it, but then the student was suddenly not interested, and then it was sitting in our lab, and I had to go to the students every group seminar and say, okay guys, who wants to use it? Nobody wants to use it. I said, if you do a good experiment, I give you 100 rupees, right? 100 rupees was not enough, so I had to increase the price tag. And now suddenly, once they know how it works, they like it, and they do it, and they try reactions. We try especially very often to do the photo reactions and reoxidize or reduce our photocatalysts to get the catalytic cycles going. And so I think it's a technique, but it's good to have as many techniques available in the lab as possible. Okay, so I think, I don't know, what is not coffee break, tea break, Debayan is going? Lunch! Lunch, you guys must be starving. Lunch, okay, but it was until 1:15, right? The original time? What was the time? No, but when was lunch break? How bad was I?
12:40 to 15. And today you don't have now class, but tomorrow.
But it says 11, yeah. So 12:45. I thought I had until 1:15. So say Debayan, I think is tell him to come half an hour later.
Yeah.
Oh God! You see, you guys are nice. You guys, in Regensburg, either the students would have been gone by now, or they would go and say, you're running heavily over. You guys are so nice and just sitting there and. God, I'm so sorry. I thought I have until 1:15. And so I thought, okay, I'm 10 minutes over. That is maybe acceptable, but I'm much more over.
Participants, but who are from here, inside IIT. Okay. And rest you are all from outside, okay? So, out of you, how many are from this state, Madhya Pradesh? 2 and 3, okay, and the rest are from others, okay. So I think that your so far things have been very nice. So are you tired of? Okay, so it's a lot of classes going on, and this thing. Okay, so what I thought that after Oliver teaches, this photochemistry, catalysis on visible light catalysis, I thought that why not we start with some other aspects of organic synthesis that we feel that which is also sustainable, and also we should go ahead knowing this, because everything stands. Today we talk about visible light catalysis, even infrared catalysis, but we should not forget the traditional catalysis what we have been doing. For example, we cannot forget how Lewis acid catalysis have helped us a lot throughout journey of the organic synthesis. So when I talk about a throughout journey of organic synthesis, I would like to highlight that how we have been going all through these years. Can you close that door? How organic synthesis have evolved. That is also a very big thing. What as a practitioners of organic synthesis we should know. Okay, so. If you see in the slide I have made, I'll start with the first few slides stating that, we think about knowledge on retrosynthetic nomenclature. So these are some knowledge competences what I feel that a student must have when he talks about, or we think about organic synthesis and catalysis. And then we come to asymmetry. So I feel that a student should have knowledge on retrosynthetic nomenclature, knowledge on mono and multi-dimensional electrosynthetic strategies, knowledge on interrelations between electrosynthetic entities and real chemical compounds, knowledge on designing synthetic routes to complex target molecules on the basis of electrosynthetic considerations. See, I always say my students, whoever have been doing or studying with me or carrying out different journeys with us, that whenever you after your training, you join academia, industry, wherever you join, the first thing, even I have told to our master students, that the first thing what your employer or your exact supervisor wants is a complete trained student. Okay, this is what is the expectation. You may pursue your education in India or in abroad. You may work in academic research institutions or you may work in industries. So what is an expectation? As a synthetic organic chemist, people expect you to be very, very competent. When I say it's competent, it means that is something called a toolbox in you. What is a toolbox as a chemist? As a chemist, the toolbox is the vocabulary, the knowledge you carry on. I've given them examples. For example, the moment you join industry and they ask that you need to make this molecule, you go to the fume hood and get a very economic strategy of this molecule. And that is the point where time matters. You cannot say to your supervisor that, okay sir, I will take 7 days to design a electrosynthetic analysis and on the 10th day, I will start the first reaction. And at the end of 1 month, I try to give you that molecule. So this is not going to work, okay, because we think about time economy. And there, the time comes where you need to understand that how beautifully you can do a retrosynthesis, how beautifully you are trained with a toolbox of reagents. The moment are going to use sodium hydride for a reaction, or going to use potassium hydride or lithium aluminum hydride, it should come in the first sense. So I want my students as practitioners of organic synthesis who take these courses that you should try to come up there where there is no time. The moment I say you that I need a reagent to go for a reduction of an alpha beta unsaturated ketone, keeping the double bond intact, you should tell me immediately, sir, this is the reagent. The moment I ask you that I want to maintain the stereochemistry intact when there is an alpha chiral center and then reduce the double bond, the moment I say you, there should be something in you where you come up, okay sir, we are going to choose sodium cyanoborohydride for this. So this is the place we want our students to come up. Okay, so with this basic introduction, I feel that these 4 portions, the 4 points, what I feel that the competencies may generate among our students are retrosynthesis, multi-dimensional retrosynthetic strategies, interrelationship between retrosynthetic entities and real compounds, and also designing very, very complex target molecules. Okay. Now, what are your performance skills? What I believe that we should grow up? They are recognition of distinctive structural patterns as key elements for retrosynthetic disconnections. In the third point, see, I have mentioned that there should be a strategic decision making based on structural features of the target molecule. See, it's a feeling, it's not memorizing. See, chemistry is a feeling. You should feel it. You cannot think that I set a reaction in a fume hood and I'll go to the hostel, ये 8 घंटा घूमने वाला है, मैं जाके सो के आ जाता हूँ. No. So there should be a feeling. It's like your baby. Okay. When you set a reaction, you feel that what is happening. Is my baby giving birth? It's growing. If growing means is a new molecule gets generating. See, you are very powerful. So who is the most powerful in nature? Mother. Okay. And how you are powerful? You are powerful because you have the art of making molecules. You can give birth to a new molecule. Okay. And I say that as babies have brains, molecules also have brains. Otherwise, an antibiotic cannot go and selectively kill certain cells and to not kill the other people. So those are molecules. So I feel, I perceive and I believe that molecules have brains. They can understand where to go up. Okay. So it's growing of your babies, which are molecules, giving birth to them and then reacting. So it's organic chemistry is a feeling, and it starts the moment you start doing the reaction. Okay. Now, so this is some of the concepts, background and terminology what I feel, and we'll go like this. We have a historical overview, we have taxonomy of retrosynthetic analysis, general aspects of retrosynthetic analysis, categorization of retrosynthetic strategies, retrosynthetic analysis of aliphatic and alicyclic compounds, and retrosynthetic analysis of aromatic compounds, and analysis of variant natural products. And I want it that when I go through, it should be interactive with you. Okay. So these are some of the stalwarts, I believe, that who have written these articles and books. They have been highly cited, and I think that every one of you should have a look. The first one is a very good collection by none other than Professor Elias James Coe, and this is the logic of chemical synthesis. Okay. The next one is, I think many of you have already read. The next one is organic synthesis, the disconnection approach. So how many of you have gone through this book? Can you put your hands up? Okay, I have gone through. No one? So this is, I think this is available, and this is already being taught in many of the undergraduate syllabus. So this book is a very handy book and gives you an understanding how you should try generating or synthesizing molecules. The third one what I have enlisted is a paper in Anglo one day by E. James Coe in 1991, where he shows very typically very strong molecules or very complex molecules to synthesize. And you see, it starts in 1991. The moment I am talking about this time when we did not have a lot of structural analytics. Today we have single crystal XRD, we have high power NMR, 600 megahertz, 500 megahertz, what not. But just try to believe that in 1991, when people used to do all these complex molecules, how they are doing it. Today, even students need just perform a one step and they run for NMR. I want you to also remember those time when organic synthesis grew and we did not have any tools of characterizing these big molecules, these complex molecules. The third one is by Walker in a very common article. This you should also go through this. And the last one, what I feel is very important, is a fantastic article in Anglo Ande by none other than Casey Nicolau. Okay, so I hope that these 5 articles, whenever you get time, you should pick up and go through any of these articles in your leisure time. Believe me, they are very nice, very informative. Okay, a short history of synthetic planning. You know all that Coe has thus been awarded with Nobel Prize for 3 intimately connecting contributions which form a whole. Through retrosynthetic analysis and introduction of new synthetic reactions, he has succeeded in preparing biologically important natural products. So he was really, fantastic. If you see Coe's contributions, then it's unimaginable that how this guy could do this type of chemistry, 100 years back. It's something which was told by Professor S. Gronovich, and who announced this during 1990s Nobel Prize Committee of Chemistry. So he told these few lines in honor of him before he was awarded Nobel Prize. So I feel that it's Elias James Coe whose contributions or whose findings laid the 19th century synthetic chemistry. What we have been doing now is just piling up on him. Okay, our contributions are really great, I'll say, but everything we can build on certain foundations. So one of these foundations is by Professor Coe, and in today's world, if I remember a young guy, then I will think of Phil Barron in the US. So I think these 2 people have shown some or given us some important pillars of organic synthesis. Okay. So if we go in the phase 1 in the 19th century, we can remember that these molecules, what are these molecules? Hohler in 1898 discovered urea. We all know urea today, right? Followed by Kolbe. I think, see, what I'm mentioning is some of, how we progressed in organic synthesis. And at the end of the time, I think you can correlate where we started and where we are. So it was our first achievement in 1828 with urea, I feel, followed by Kolbe's synthesis of acetic acid in 1845, and then comes Fischer. So you know Fischer? There were two Fischers. Interesting thing. There were two Fischers. One is the Fischer who discovered glucose, and there was another Fischer. Who was that? Sorry? Fischer projection. There was, what happens? There are some competitions. So in batches, when we did masters, we had competitions. My friend used to think that I'm a better student than him. He used to think I'm a better student than me. Ye natural hai, ye hota hai. And these two Fischers, there are competitions. Both these Fischers always is competed who has first designed the arrow. We do in organic synthesis, right? A arrow B. We do this, right? A, B. So what is A? A is a starting product. And what is this? There is another arrow. What is this? So all these arrows have resemblances, right? Okay. So what do we call this? When we use this? In retrosynthetic analysis. And both these Fischers, they competed throughout their lives that which Fischer developed these arrows first. Okay. And this was one competition. Another competition was between Woodward and Fischer, that who actually designed the structure of chlorophyll. Okay. So all these competitions are happening and they're healthy competitions. Okay. So it all started from very beginning. So how do I erase it? I don't know. Can we erase it? Okay.
Eraser.
Okay, thank you. Okay, so we started with reactions designing anthracene. You can see this, this is anthracene, okay, and small oxidations like potassium chromate, sulfuric acid, we generate alizarin. So if you see, the key features are that synthetic organic chemistry focused on the analysis of simple intern conversions of small molecules and coincident discoveries. Very little structural information available those times. So you can see that I have given a journal, I collected this from this journal in 1869. So only empirical formulas. So we started our journey as synthetic chemists from here. Okay, it's the earlier 19th century. Also, we find that we generate molecules, we generate synthesis like ammonia and oxyacetylnitrile, hydrocyanil and hydroxycyanide and giving urea. So this basic transformations were the one which were carried out during those times. Okay, I'll quickly pass to the next one. When we started going towards some more complexities, like the one I showed, that anthracene you oxidized with potassium chromate and sulfuric acid, and now we were in a place to understand what is actually alizarin with the help of the functional groups. Okay, so how do you understand functional groups without NMR? How can you do it? How can you understand that there is a group called carbonyl, there is a phenolic OH, and I say you that you have nothing in your hands. You don't have IR, you don't have NMR. How you are going to find out? Because it was not available in this time. people were understanding that the chemistry was dominated by aromatics, particularly from coal tar. Now, I tell you a very important information. Try to understand. Today we are in a position where we should shift our chemistry. Why I say that? Our chemistry was always oil driven. Is that correct or not? It's oil driven, because what we come is all non-renewable resources. So you generate hydrocarbons and then try to functionalize these hydrocarbons. And what is the source of these hydrocarbons? The source of the hydrocarbons is always an oil. Is not so? You get everything from oil. You try to understand. But where we stand now? So there is a time that we change our chemistry. We change our chemistry from oil-driven chemistry to biomass-related chemistry. Is not so? We should come up, right? Because we know that 10 years, 15 years, 20 years, what will happen to us after 25 years when the oil is gone? Where you get these hydrocarbons which we want to functionalize? Where you get this, oxidized molecules? Because ultimately the source is oil. Okay. So we started from oil, basically coal tar, and then we tried to functionalize. We did not have NMR, we didn't have IR, we did some oxidations, and slowly a time came, then we started using some chemicals to understand, okay, there is a carbonyl and the chemistry is dominated by aromatics, there is phenolic OH and nothing else. So this was what we were understanding on the phase 1 phase. So this is the first phase of organic synthesis in 19th century. Okay. Now then comes the early 20th century, very beautiful time. Why? Because here we start growing up, the entire world starts growing up in synthetic chemistry. Perfumes start coming up as a very important molecules in Europe, So we needed molecules, we needed sesquiterpenes because very high demands, particularly in European countries, on cosmetics, on perfumes. So people tried to get new molecules, tried to increase the molecular complexity. And you see, Will Slater in 1901 comes up along with Robinson. So I think both of them synthesized first tropinone. So why this molecule was important? Because we started finding a three-dimensionality here. So we started increasing the knowledge on structural, empirical and structural formulas. We tried to think on the tetrahedral model. We tried to think on increasing synthesis of non-polar target molecules. So we tried to come towards more molecular complexity. We are no more on urea. We have started thinking on visualizing three-dimensional molecules which were important to the human race. Also, camphor. We all know why camphor is important. So these were start coming up. But you remember one thing, we did not start doing multi-step synthesis. This comes later. We started understanding that these were some three-dimensional molecules and that can be used in industry. We started understanding that. Also came up something called the very important one by Fischer in 1929, which is called hemine. And we all know why it is important. Why it's important? Because it forms the basis of something called porphyrins, right? Why porphyrins are necessary? Because we all know what are the bioactivities, what is inside us, who are the oxygen carriers. So it was the first phase of early 20th century, and we call it phase 2 of organic synthesis, where we started understanding these molecules. And please try to understand that we should always understand the contributions. See, Perkin in 1904 developed the alpha terpineol. So we read alpha terpineol in natural product synthesis. So see, we had important contributions by Robinson, Perkin and Fischer. It started in the early 20th century. Now, if today's world, so we are all we are all equipped with NMR, mass, everything. Now, if I say you that I want to generate tropinone, which was synthesized by Will Slater in 1901, and I give you cycloheptanone, you try to make it. How you make it? So you join an industry, and the same guy who is there in the industry, who is your boss and group leader, asks you, go to the film wood and make tropinone today, which was synthesized in 1901. And it was done by 16 linear steps. You do it in 3 steps. What would be your answer? How do you think? How do you start thinking it? Can we make it? Can we make tropinone from cycloheptanone in 3 steps? Is it possible? Okay. So, what will be the starting step? Any idea? You have cycloheptanone and you want to have 3 steps to make tropinone in 3 steps. And what is the first step I am asking from you? Okay. This is the way that it was made earlier. So, you start with a cycloheptanone and you do a reaction like hydroxylamine and then treat with sodium ethanol. I am not going into details, but you see there are a series of steps which gives you something like this. So, what will be the name of this? Anyone from the MSc? I want some interaction. Even the early PhDs. What will be the name? So, Arindam, what is the name for this? Anyone from your side? What would be the name for the last, we generate a salt. What would be the name for this? Shall we call dimethyl amino tropinol chloride or what it is? Okay. So, we keep something for tutorials. Okay. Now, so we generate this salt, heat it so that there is a liberation of methyl chloride, and through these steps, so there I am not saying you or explaining you all these steps. So there is something, we eliminate, we go for anhydrobromination, then we replace the bromide in sulfuric acid conditions, and finally the chromic acid oxidation gives you this product. But what was important was the last line. Please try to see. Reaction sequence is predominantly linear. So they were linear steps. We didn't have stereochemical considerations. So in the phase 2 of organic synthesis, we went into some complexities. We came up with 3-dimensional molecules, but we were not in a place where we started thinking of asymmetric centers. Okay, so what is asymmetric center? What is asymmetric? What do you mean by asymmetric? Anyone? So, do you know what is asymmetric? Anyone can put your hands that, yeah, I know asymmetric. What is an asymmetric center? Okay, yes. So, he says that it's a designated chiral center. When is its chiral center? Then what is a pro-chiral center? So, we generate an asymmetric center from a center which is not chiral, is a pro-chiral center. Is it like that? Okay. Now, so Robinson in okay, can you see the yellow color? Okay. Robinson in 1917, he said that by imaginary hydrolysis at points indicated by dot lines, so there were some dot lines here, okay, and the substance may be resolved into succinylide, methylamine and acetone. So he said in 1917 that if I plan to make tropinone, first I should try that where I should cut the bonds. Okay, so this was something what Robinson planned in 1917. He looked like, so there was nothing called retro. He imagined, so it's an imaginary hydrolysis, that if he thinks that if he cuts these points, okay, you generate something like an aldehyde, methylamine and acetone, and this suggested a line of attack and nothing else. So the first thinking of retrosynthetic analysis comes in 1917 from none other than Robinson himself, who started thinking that how to break a tropinone. And in the process, he thinks that he generates an aldehyde, methylamine and acetone, and that is nothing but an advent of retrosynthetic thinking. So if I ask you that when did we as a chemist started thinking the concept of retrosynthesis, then it's nothing which comes with Robinson's thinking in 1917. So we should be clear with our developments. So it's 1917 which taught us, which was the first idea that, okay, if I cut the bonds of tropinone, which was actually synthesized long before by Will Slater in 1901, but all these 16 years, no one thought what is retrosynthesis, how to cut the molecules. So it was first by a very big shot, Robinson. It's 1917. And if you search in Google, as I told you, that there has been always competition between chemists. If you search something by typing, competition of two Roberts, then you will find one is Robert Robinson and the other Robert you should find out. Okay. So there were two Roberts who fought each other in telling the world that who has first synthesized steroid. One is Robert Robinson, the other one you should find out. Okay. You should also do some activities during your Gian course. Now, what he actually meant was, if you have this aldehyde and a methylamine and you do a one-step reaction, then you should end up with something like tropinone. Okay, this is a one-step transformation which was planned by Robinson in 1917, and this is where we successfully tried to cleave the molecules and make the molecule and understand that, okay, this way we should approach any molecules to be given us. Okay, phase 3, the mid of 20th century, and we call it as the phase 3 of organic synthesis. What do you see in the slide? We started with urea, right? The human race started with urea, and now if you see all these 5 molecules, a name has been written in the end of this molecule. Who is this guy? He's a guy who died early, but did a lot things that we did not have a second Woodward in the world. Okay, so he's a guy who was already awarded Nobel Prize in 1965, and his name was Robert Burns Woodward, and he tried to go for structural elucidation using IR and NMR spectroscopy, combustion techniques, melting points, ultraviolet techniques. But see that from where we migrated, we were thinking of tropinone in 1917, and in the mid of 20th century, in 1944, 1950, 1951, 1954 and 1966, an antibiotic comes forward with Woodward, which we use till now. It is cephalosporin C. This was a point where we started using plus minus. What is this plus minus? Plus minus is what? Racemic mixture. So now you please try to understand that this was a time. So by 1944, we started understanding that there were something called racemic mixtures in the molecules. Okay, so we tried understanding the stereochemistry slowly now. We're getting the masters, we're becoming the masters of chemistry, understanding that these are complex molecules. See what was strychnine, so complex, and it was Woodward in 1954. How many chiral centers? 1, 2, 3, 4, 5. He tried synthesizing these molecules in his lab with his group of students. See cephalosporin C, very tough, because you have a 6-membered and a 4-membered lactam with it joined together. We can easily synthesize it today, but in 1966, with limited facilities and limited reagents, Woodward was the person and his lab was a group who synthesized all these challenging molecules starting from quinine, cortisone, strychnine and cephalosporin. So this way, from 1944 to 1966, Woodward's group in the US was a group who actually pioneered the synthesis or completed the synthesis of very, very complex molecules. This is a place, this was a time then really the synthetic chemists were always in the show throughout the globe. Okay, everywhere they were treated as kings, because just see their perseverance, see their hard work. All these molecules were required in the globe because these are all biologically active. No? This quinine is a very important, pharmaceutically important drug, and the whole world wanted that. So how are we going to get it if the synthetic chemist is not designing strategies to get it, because natural resources are less. Okay, so this is what happened in mid-20th century, and we started understanding that there were stereogenic carbon centers. So these were the carbon centers what we tried to visualize. Okay, stereogenic carbon centers. Okay, very good. Now if I ask you a simple question, I have a starting point like isoquinoline 7-ol, and you are a student of Woodward in 1944, and you need to make it, and your boss says that okay, you need to make this molecule. How are you going to make it? You have to make it, otherwise you will not get your PhD. How you are going to make it? Okay, so there we start thinking synthesis planning was markedly guided by degradation studies, a standard candle what I call along synthetic route. So it was like a candle, okay, and it was giving some light out of the darkness, and it was guided with building blocks. Okay, so it was nothing like creation of these beautiful steps. So we started understanding that okay, this way we are going to break the molecules. We start isoquinoline, then N-methyl isoquinoline 7-ol, then a dearomatized skeleton and a quinoniclide precursor, finally heading up to quinoine. So this is what is the starting material, what Woodward wanted to do, and then go towards this. But I would say that if you read Woodward's paper on this, their strategic rationale still remains unclear because there are many other alternatives. So the only thing is what we can understand that this is not the best synthesis what Woodward had prescribed in his paper of quinine. There are many other simultaneous syntheses, but I feel that personally the reagent availability or the availability of the starting materials in the US in that time in 1944 had restricted him to go all the way around in so much of tiring reactions. Okay. Today we want to synthesize a strategy which is of any molecule which will be easily accepted by industries. See, industries are not going to accept you like anything. They raise questions on your retrosynthetic analysis, that how economic it is, how fast it is. In our laboratory, we think of a reaction called dearomatization. My students are sitting here. We think that we need the reaction to be done in 10 minutes. We cannot compensate 2 hours for it. This is the scenario today, but we have not reached in one day. It is all through all these years that today we are discussing the past because we need to understand the present. where we have come through. Okay. Now, so just a question that if this is not the strategy, okay, we start from isoquinoline 7-ol and then come to quinine. So 1, 2, 3, 4 and 5. If this is not the strategy and you use the same starting material, and if I said it's 2 steps to this, what would be the reaction? Did you get my question? My question is, this is the starting material you're using, or isoquinoline 7-ol, and Woodward has given 1, 2, 3, 4 steps. I want to do it 2 steps. This is important because I'm going to raise a question on you for examination. We will be doing grading on that. So 2 steps. So Sangeeta will be sharing the slides. 2 steps starting from isoquinoline to quinine, not all the way around, because I have already told you that the rationale by Woodward remains unclear that why he has used long, So please find a strategy in your minds, or you practice, or you whenever you complete the course today, just think of this reaction which will be completed in 2 steps, not all these steps. You start from the same material, starting material at isoquinoline 7-ol and reach quinine, but you can use only 2 steps. This remains a question to the Gian students, okay? Now, the phase 4 of organic synthesis, you see extraordinary complexity of molecules. Can you see the molecules here? Elias James Corey, Kishi, Nicolau Corey. See, I often love to tell you stories to all my students. Tetrodotoxin is a molecule. So if I ask you what is the most poisonous molecule in the world, what will you say me? What will you say me? Yes. What is the most toxic molecule in the world, available in the globe now? What will you say me? Is it potassium cyanide? Is it potassium cyanide? Sorry? Is it potassium cyanide? Many students say me, sir, it's potassium cyanide. You just take it in, 1 minute you're gone, because it traps all the oxygen and, it removes the coordination of oxygen, okay? Because the cyanide is a better coordinating to your iron in your hemoglobin. So it's not. It's the one molecule which is synthesized by Kishi, Yoshito Kishi, and it's called tetrodotoxin. It's available in the skin of the puffer fish. So this molecule was designed or synthesized by Kishi in 1972, which is actually the most toxic molecule known till today. And they have a fantastic relationship. Corey and Kishi, I'll tell you why. But before that, you see the molecules, Nicolau, see the, it looks like a basket, isn't it? But just think that how to make this molecule, very tough. See the number of chiral centers, just see that imagining this molecule is so complicated. And if I ask you to design a retrosynthesis of this molecule, how complicated it is, and when it is in 1988, it's not in 2025. So try to understand that how people is to, first you need to visualize the molecule, understand the structure, chiral centers 1, 2, 3, 4, 5, 6, 7, 8, so many chiral centers. So if you have 8 chiral centers, how many enantiomers you are going to have? 2 to the power 8. And out of these enantiomers, 1 is pharmaceutically very, very active, which shows you those properties. And you need to design a retro which will exactly synthesize this stereochemistry. Okay, the relationship with Kishi and Corey is that Kishi was a researcher in Japan, and the moment he delivered his lecture of tetrodotoxin in a conference, that how he made this complicated molecule, and after his lecture, Corey was so happy that this young guy has done completed synthesis of so strong molecule. he immediately offered him position as an assistant professor in Howard University. And from that time, Kishi is still now, he is in Howard University. Okay. I know all this because I am a student of Barry Trost. Okay. Barry Trost is in Stanford. I did my postdoc in Stanford, and Barry is also very old. Okay. So he was actually in touch of all these people, and I used to see that these people used to come there and visit and all that. So I know the stories from that time. Okay. So Kishi is just because of this molecule, when he synthesized and he showed that he could have, he made it, then Kore was so happy with his work that this young guy could do such a complex molecule. He's deserved to be in none other than Howard University for his rest of his career. So it's your work which gives you a lot of recognition. Okay. Now, so you need to increasingly, so at this moment we need to understand that we have started the sophisticacy in the molecular design. So we were entering the sophisticated era of molecular designs, molecule designing. Okay. So just as I told you in my starting of my class, just imagine that how strong you are. Okay. How strong you are because you are a person who has the capability of making this molecule. The rest of the world doesn't have. Okay. Now, the key questions. So, what has raised in my mind, and I have taken up these questions after I went through the logic of chemical synthesis by E.J. Kore, and I think these questions will rise in every one of his mind. The questions are: how does modern toll synthesis differ from historic approaches, and what can we learn from that? How do we rationalize the synthetic approach to complex molecules? And what are the guiding considerations when planning a synthesis? Okay. So, I'll just take 2 minutes to ask any of you if you want to answer that. So, in the last 27 slides, okay, what do you think? How does the modern toll synthesis means the same thing. You start from a small molecule and reach a complex molecule. How does a modern toll synthesis differ from the historical approaches? What do you think? Anyone from MSc? How do you think? You went through the last 27 slides and you also saw that what I have done a gist of everything, a summary of everything, because if I catch one phase, each phase of organic synthesis, that itself will take 4 or 5 classes. Okay. So how does toll synthesis differ from the historical approaches? What do you think? Today's approaches. What? Any idea? You should think. The first idea what I feel is that, and that is sustainability. Don't you think that we, as I mentioned you, that we are going short on our raw material supply because we are going short with non-renewable sources of energy, and all this synthesis, all these starting materials, whatever chemical companies it can be Sigma Aldrich, whatever it is, they are supplying us starting materials which actually are derived from these oil-based chemistries. And this is a place that we need to shift our paradigm from the oil-based chemicals to biomass, because biomass is glucose, furfuryls, oxycycles, pyridines. We need to have those starting materials in the toll synthesis. For example, we need to start thinking that I will pick up some dry grass from the ground and put in a reaction and get a molecule. Or I use this plastic, take this, scratch it and put in an RB and then do a reaction, and we get the next step of a complex molecule. So we should slowly shift off this paradigm from this portion to this. But again, I did not tell you one more important thing. Okay, what I say is this is the raw material I'm talking about, but what about the strategies? If you remember, if you understand, if you try to find a cost of the most employable catalyst across the globe in industries, what is that? And which is that reaction? Can you tell me? Any idea? The reaction, yeah? The reaction is hydrogenation. The reaction is hydrogenation in one side when you reduce a double bond to an alkane, and the other side is, yes, to some extent, but modern industries are coupling reactions, okay, Higgs couplings, but you use what catalyst in both these cases? Palladium. Different phases of palladium. If you go to hydrogenation, you use palladium charcoal. Did you ever know that what is the price of palladium charcoal? I'll tell you. Can you tell me? Can you tell Sangeeta? What is the price of palladium charcoal we use? Anyone? Ramakant? I tell you. We buy in our lab 10 grams of palladium charcoal, 10%. 10% means it's only 10% of palladium. And we buy with GST 17,000 rupees. We are a small laboratory. Our laboratory has 15 PhD students and master students, okay, and some people. So our strength of our lab is 20 in my research lab. Now just think an industry where 500 employees and scientists are working, only one industry, and hydrogenation they are doing in tons. Just understand the amount of palladium being used and purchased. On the other side, the coupling rate is also very high. You visit any industry. I always visit industries because I have been a very invited. I'm very lucky to be invited to very many industries. I visited AstraZeneca, I visited Middlesex Industries, I visited Anbaxi. We work closely with Dr. Reddy's. We know it. So we have a place now where we need to shift from the reagent-based chemistry or metal-based chemistry to what? To what? Sustainable chemistry. What is that? What is that? That is nothing but light. That is nothing but electricity. So electro-organic chemistry and visible light chemistry. I'm not talking about UV. We cannot use. That's environmentally not allowed. So I think that if we want to rationalize and if we want to understand that where we should shift or how does the modern toll synthesis differ, that's only and only sustainability, so that we should, as a chemist, we should not be called now and a community which uses the solvents and dumps the solvent in the environment which we cannot sustain. We should shift to a place where we should plan all this toll synthesis from a starting material like plastics. This is the point what we need, okay? Very good. So what is the time of this class up to? 3? Okay. Okay, now coming to the general aspects of retrosynthetic analysis. I have like lot of things, so I don't know. Okay, let's go fast. So what is the traditional approach? The one I show in the screen. What is SM? You all know. What is something called a starting material in a chemical reaction, right? And something we give a double arrow and we write intermediate, and then some more synthetic arrows and we call it what? Target molecule, right? So this is something we think of a forward reaction, and Corey says that we focus on something in the process called FG. What is FG? Functional groups. Very nice. You know everything. Very nice. Okay. Now, so the left side is a traditional approach. Starting material, intermediates, synthetic arrows, and target molecules. What is the modern approach? We go reverse. Starting material, intermediates, and target molecule. So this is what we talk about, the retrosynthetic arrows. Okay? Very easy, very nice. We all understand this. And we call it a guiding principle called retrosynthetic analysis. Very nice. Now, I come up a question. Okay? You see this molecule. Very nice molecule, 6-membered, 2 diketones, 2 esters, fantastic. Now, which one is best? I want to make this molecule, and we cut this molecule as A, B and C, because by this time you know how to cut molecules now. And I ask you a simple question, which one would be the best? A, B, C. B. Why? Let's find it. Okay. So if we go for A, then we generate some intermediates like this. Okay. So we have a positive charge here, and we have a positive charge here, and we have C and minus because they should combine. So it should be opposite charges, right? Is that correct? So this is which comes off after we cut A. Now the next one, if we cut B, what do we get? We get something like this. We have the same thing. We have a negative charge here, we have a positive charge here, we also have a positive charge in the alpha acyl group and negative charge here. Fine. And if we cut C, then we have something like this, which is also intermediate. And I ask you that Arindam says that B is the best. Why? If you see the overall plan, it's nothing. In all these three cases, what we try to find is overall plan to reach a final target material, identification of efficient disconnections, and identification of suitable transforms. These are the three things we want. And then we have a situation that either we're going to cut the molecule this way, either we're going to cut the molecule this way or this way. Which is the best and why? So your voting is for B. I think Oliver planned very nice softwares. Huh? You are all voting. I have to learn it from him. Okay. So this was B, right? Is it B? Anyone from this side? Is it A, B or C? Which is the best one you are going to choose? Obviously there is symmetry, I understand. Okay, sorry. Which is the best among this? And I need a proper explanation. So I'll ask Arindam. Arindam said it's B. Why it's B? Can you speak louder so that everyone can listen? That's a very perfect point he picks up. He said that if you have a minus here, then actually this methylene is actually flanked in both sides by two electron withdrawing groups, and then this is actually stabilized. Do I find any other stabilization here? Here there is a stabilization, but there is a negative effect. We also have a stabilization here, but we have a negative effect, and negative effect is having a acyl carbocation, which is actually an unstable one. Okay, whereas we do find it here too, but in both these parts, this is what is actually stabilizing the intermediate B much better than the other two. Is it correct? Yeah. So that means that we need to choose this retrosynthetic analysis because we need to have a very successful reaction. And then what will be a starting material? It's very easy. So your starting material should be someone which has a positive one, which if you have, you can take a chlorides from this side or you can take a methyl in this side. Okay, is that correct? Or you have any other opinion? Is the B correct? Okay, very nice. Now, sorry, what about this molecule? It's antimicrobial molecule, and I need something like having an hidden symmetry. Okay, what is an hidden symmetry? Just try to have a look. In this molecule, we had an obvious symmetry, which was very, the moment you see this molecule, you recognize it. The next molecule I pick up, I call it that there is an hidden symmetry. The hidden symmetry comes from where? The hidden symmetry comes the moment I cleave this bond and we generate two double bonds like this. So here lies the point that can you come up with a step which gives you an hidden symmetry while solving the retrosynthetic analysis of a molecule. Okay. So the hidden symmetry is very important. You need to understand that if I can come up with a hidden symmetry so that you can use the same type of molecules in both sides. There are many people, many good synthetic chemists, even Kore Nikolan in India. If you see Professor Alakesh Bishai from IISER Kolkata, you'll find that all his molecules, what he designs is based on Kore's principle. The moment you look the molecule, it looks very, very complicated. But the moment you find the hidden symmetry, actually you are going to use only one molecule for the synthesis. There's just dimerization. So this is where your perseverance comes in. You need to find out that if there is something like an hidden symmetry in the molecule, and that gives you just nothing, but you just take one molecule, create a positive and negative charge, and thus just dimerize, you get the best precursor to go towards your target material. Okay. Now, the next thing, examples or presence of functional groups, very sensitive to a nucleophilic attack. So, when I say this strategy, okay, we have different strategies to look into the molecules. So, can you see any important functional group in this molecule which I have drawn? And what is that? Can you highlight? Michael acceptors. See, Michael acceptors in organic synthesis have played very, very important role in solving molecular complexities. So, I would like to give a message to all of you that whenever you start your own chemistry, always try to think that can we start a molecule where there is a Michael acceptor, very reactive one. Why do I say this? Because I have personally found it that if you have this type of systems where there is a Michael acceptor, what is a Michael acceptor? Where you can undergo 1,2 additions and also 1,4 additions. And if you plan for a synthesis of big molecule and you are confused that where I need to start, in such cases, having intermediates or having molecules as a starting material which have reactive Michael acceptors is a very, very good choice, because it gives you immense independence to make this molecule very complex. You can use it in any methodology. If you do a one-step reaction for any journal, for any paper, and your teacher asks you, can you go for functionalization? Can you do something in the paper that the research paper looks very interesting? Then I will always choose a Michael acceptor, or rather a cyclic Michael acceptor like this. You do whatever you want to do in your paper, you do. But at the end of the paper, in the functionalization, in order to show very, very huge applicability of your science, this is what is very important, very sensitive to nucleophilic attack, should be installed in the late stage. What does it mean? It means that it is so reactive that whatever reaction you do, and if you install the system in your molecule, it can show variety of variations. And this is very much required. See, today if you want to publish a paper in Jackson Anglo-Vanda, the first thing is, what is the application of your paper? And how do you show it? You show it in the application when you prove that yes, my methodology can create a lot of important biologically active molecules. But how you are going to do it? You have less time. In such cases, you should use such reactive intermediates. Okay, but how do you make such molecules? And it's not easy to make such molecules which are reactive. Okay. So what is the beauty of cyclopropane? What is the beauty of cyclopropane? The beauty is that you use it in radical reactions, you use it in heat, you use it in visible light, it will open up, right? Why? Okay, it's very open. So रमाकांत बहुत शांत लड़का है, शांत लड़का है, एंड द अदर गाय इन माई लैब इज वेरी हॉट माइंडेड, कभी भी लड़ता है, हु इज बेटर? आप पूछ सकते हो सर आप क्या क्वेश्चन कर रहे हो, हु इज बेटर? साइक्लोप्रोपेन इज ऑल्सो लाइक दैट. To make cyclopropane is tough, is not it so? But you see the usefulness of cyclopropane. So that means in chemistry, when you want to make reactive molecules, making these molecules is also not easy. So when you think of alpha beta unsaturated ketone like this, we need some specialized reactions like Eisenhower methylation, and it can be done in one single step. You use this, this 5-membered lactone and react, and you get it. Now, okay, very nice. Can you see this molecule? It's quasine, bittering agent. What is bittering agent? Why it is used? It is used in drugs which is prescribed. Many companies advertise them as, you can give this thing to someone who wants to who want to get free from nicotine. Okay. This is the most bad thing what organic chemists have developed till now, what I feel. Although it is very active in entertainment industry, but it's not correct. So quasine is one of the molecules which is prescribed to people who want to quit smoking. Okay, bittering test. But you see the molecules. There are 7 stereogenic centers. How to control them? Do all the stereo centers need to be externally controlled? Now, how do you make this molecule? Because there is a huge industrial demand. Even the ITC wants to make it. What is ITC? Yeah, there are 2. One is Indian Tourism Corporation, the other is Indian Tobacco Corporation. One of the most, So how do you want it? How do you make it? So I tell one of the students, go to the lab and make this molecule. What will be the retrosynthetic analysis? 7 stereogenic centers. How many enantiomers possible? 2 to the power 7. What is the number? I did not calculate, but you can calculate 2 to the power 7 enantiomers. But see the stereoisomers. This hydrogen and this methyl is cis. This hydrogen and this hydrogen is trans. This hydrogen and this methyl is trans. This methyl and this hydrogen is cis, and this 1,3 hydrogen are trans. So you have this molecule. You have to make this molecule, but retaining all these 7 stereogenic centers. So this is one out of these 2 to the power 7 enantiomers which is bioactive, and we say it's configurationally unstable. Why it's unstable? Because lot of chiral centers, you cannot expect that how much stability it gains while synthesis. Okay. So I point something like, I will come to this point again, I think next class or tomorrow's class, something like thermodynamic control. So what is the difference between kinetic control and thermodynamic control? What do you mean? आसान भाषा में बताओ. Kinetic stability, thermodynamic stability. Shall I give you an example? I'll try to explain you in this way. You are standing in a bus stand and a bus comes, and suppose Arindam is standing and the bus stands in front of you, bus is fully packed and there is one lady seat, okay, and Arindam is a male and he is thinking to sit or not. If it's a kinetic condition, he will sit. Now the same condition is, the bus comes, the bus is purely vacant, there is window seat, there is front seat, and then Arindam chooses a window seat and sits there. What is this? This is thermodynamic stability. Okay. Understood the difference or not? The first one is a compulsion. What we called is kinetic stability. And what is the second one? Is relaxing mood, is an honor, is like something, you choose the best for you. This is what is thermodynamic stability. So when I say that the purple one, okay, is something which is configurationally labile, can be cis, can be trans, And the purple centers are under thermodynamic control. Pink centers are to be set by substrate reagent or catalyst control. What does it mean? It means that when we have these complex molecules, we need to understand that which centers are configurationally settled. For example, you have an umbrella. Just think about an umbrella. Umbrella is like this. So if you see inside, it is something like concave, and if you see from up, it's convex. Now, if there are two methyls in the upper side of the umbrella, then both will be definitely cis. It cannot be trans. So that is what is substrate controlled. So by default, if you generate two centers in the convex portion of an umbrella, there by default it's going to be cis. It cannot be trans. So it's something like substrate controlled by default. It's a topography of the molecule. And the one, if you want to synthesize one up and the one below, okay, it's again, it should be trans. It's again a substrate control. But now you want to make a cis and trans. So a trans in the convex type, there comes something like a reagent, substrate, or a catalyst control. So you have to control that stereochemistry. So when we come across these molecules, then first thing we need to identify that what is by default, and we call it thermodynamic control. It's already there, whatever you do, this will be cis. The next is how are you going to generate the trans when, or you want to selectively generate the trans when there is an equal possibility. That is what is reagent, reagent or catalyst control. Okay. Okay, so I'll just quickly pass in. Yeah. Okay. Okay, we have a tea break. Okay, then we'll come back. Okay. Thank you. Okay, I think you can join. There's tea already. Then you can have a tea, and you also have a tea. And if you have time, can sit back, the MSc people, or you can go for your next class. Okay, but I continue with them. I think you can come forward to sit so you can interact. Okay. So I think like we start the next part because although I had many things like on the first part, which is retrosynthetic analysis, how to make molecules. So I have instructed the students to post you up all the slides. So I have I have bought many slides, but I think looking into the interest of time, I need to teach you the other portion, what we have mentioned in the Gian course. And that is something like the asymmetric synthesis and catalysis. I feel that this concept should also come up. So in the first class, I showed you that where we started, like how do we started organic synthesis and where we are, and now at the present scenario, what type of sustainable synthesis we are thinking on. So organic chemistry is a pillar. So the pillars are reactions, stereochemistry, reagents, which are your toolboxes, and your understanding to approach a molecule through retrosynthetic analysis. With this, parallelly goes something very important, which is called asymmetric synthesis. And as we are discussing, that asymmetric synthesis means generation of new chiral centers. And in the last examples, you saw that what type of molecules you have. A lot of molecules with a lot of chiral centers, and we need to think that how we need to make them, and also with high enantiomer selectivity. Okay. The other concept is catalysis. We are all familiar with this word because this is where we employ a small amount of a reagent in the reaction, which make it faster, which make it better yielding, and that's why asymmetric synthesis and catalysis should go together so that we can achieve 100% atom economy. What is atom economy? Atom economy means we should have any atom wastage. Who has coined it? Who has coined the term atom economy? Atom economy was coined in 1991 by Professor Barry M. Trost of Stanford. Okay, so he's the first person who's coined the word, atom economy, and this is the place where catalysis was given a new name. Okay. Now, with coming on the introduction, of asymmetric, you are all familiar with all this, all these pictures which resemble chirality in nature and which are macroscopic, isn't it? You see the conch shells, the cacti picture I have given, the hands. Okay, I personally like all these pictures, the way they are kept, the sandals. I could not give, I feel the wrapping of a sari is also, something a chirality in nature, but I could not find a good picture. Golf sticks, hockey sticks kept in this way. These are all chirality in a macroscopic, way in the nature we find. So when we come to the microscopic level and chirality in nature, we can think of two things. One is, which is molecular, and the other thing is supramolecular, big molecules. Okay. So in the molecular side, we can think of amino acids, monosaccharides, alkaloids and steroids in the natural products, which we feel resemble fantastic chiralities in nature. When we go for supramoleculars, we can think of protein, nucleic acids, carbohydrates and lipids. Fine. Is chirality manifested in biology? Yes. So biology and chirality have a very strong connection, like where two persons are doing a handshake like this. So both of them cannot exist without the other, what I feel. How? Is there any examples? There are a lot of examples, but chirality manifested in biology can be found when you think about an enzyme substrate recognition, how an enzyme works with substrates. Second is a drug receptor recognition, sense of taste, odor, pheromones, hormone receptor recognition. So all this are nothing but chirality mentioned in biology. Otherwise, there can be no existence of this type of interactions. Human beings would have been not called the living beings if this beautiful combination doesn't work, chirality and biology. Okay, the pheromones, olein, okay, it's a sex pheromone of the olive fly, and you see the pheromone is so beautifully chiral in nature. Okay, and this is what I think the best resemblance of a pheromone, a chirality in biology. And if you see the mirror images, the left side mirror image is an isomer which attracts the males. Okay, and the right side is a mirror image which attracts the females. So this is what is chirality in biology. Okay, so we all know this, elements of molecular chirality in organic compounds. So tetrahedral chiral carbon, we can have an axis, we all know, and you can have the rotations, keep rotating, there are mirror images, and we call it configurations or conformations also in some cases. We also have molecules where actually we don't find chiral centers, although the molecules are chiral, right? Like the biphenyls, like the allenes. This is a beautiful molecule, beautiful molecule. You can do a lot of good reactions, very nice stereochemical reactions. One of the best used molecules in industries now, believe me. There is one industry in Nagpur just set up 2 years before. They are doing only chemistry with chiral allenes. And in the last 2 years, the industry has grown up like anything. So very beautiful. So we should learn, I am telling you about the, toolboxes. A chemistry student is a powerful student when he knows the toolbox and he knows how to use the toolbox. So for a long time, people have not used these chiral allenes. That industry has started taking up these chiral allenes. They're making a lot of nice molecules. They have sent me a small, prospectus of their compounds just for their advertisement. I was going through very beautiful molecules. Okay. Not only this, one of the most useful, asymmetric ligands like binaps, that's just arises chirality because there is a steric hindrance across this bond, right? So what we call is R binap and S binap, very important ligands, very cheaply available, but fantastic enantioselective inductions, planar chirality. What is this called? This might be a very known molecule to you. Ferrocenes, okay, organometallics, okay. So what was the first organometallic compound which was awarded Nobel Prize? Do you remember? First organometallic compound which was, and the scientist who was awarded the Nobel Prize. Just keep your vocabulary on. Who was that? Who was Alfred Werner? He developed something called Werner complex. Okay. Okay. Now, now if we just do some recalling of our existing knowledge, then you will find that the stereoisomers can be divided into two things. One is diastereomer and the other is enantiomer. So diastereomers have different physical property. They are separable by chromatography or fractional distillation. And third is the NMR spectral pattern is different from each other. So when there are diastereomers, they have different physical properties. They can be separated when you do columns and they will have different NMR patterns. Clear? When you come to enantiomer, they have identical physical properties. They interact only with plain polarized light, what we call as polarimeter. They have different optical rotations, and the NMR is also identical to each other. So these are also necessary because these properties help us to understand that after we do a reaction, we discussed a lot of how we approach a reaction, how we design a reaction. But what about when you get the product? We need to understand the product. We need to identify the product. We need to run to NMR. We need to see the NMR pattern and then say that, okay, this is our product. See, there are 3 steps. As a student, as a researcher, all of us have to maintain 3 things in our lab. The first thing is thinking about the reaction. I will never support a concept that you hurriedly say 10 reactions. No, you should have a complete overview like retrosynthetic analysis. You should think the reaction about 2 days before setting a reaction. Don't go and run and set 10 reactions. That's not going to work. The first thing is setting up the reaction, approaching the reaction that we discussed, how to approach the starting material, how to choose it. The second, I am continuously saying you, toolbox, which reagent you are going to use. The third is structural understanding of the compound or identifying the compound. I have seen large number of students that they have got the product in their hands, but because of not having proper knowledge on identifying the compound, they have not identified it. And if they have not identified the first compound, just understand that when you are planning multiple step sequences, if you miss one compound in your PhD or in your master's studies, you are unable to do a bigger work. So first thing is the correct retrosynthetic analysis, second is the toolbox, and the third is identifying your product. This is also very necessary. You should not leave your compound until and unless you identify it. Sir, ये उल्टा सीधा कुछ हो गया है. This concept I have seen in our student is not correct. Even if you don't identify the product based on these characterizations, try to understand what has happened in your reaction. This is very, very necessary. Okay. Now, we need to understand what has happened, and we need to also understand when you talk about enantiomeric excess, particularly in asymmetric synthesis. Enantiomeric excess is a simple calculation, what I see, that which enantiomer is more in the mixture. This is what is asymmetric synthesis coming in, that you need to have a reaction which has to be stereoselective. So, what is the difference between stereospecific and stereoselective? Stereospecific means that you have a substrate which gives one enantiomer in excess. So, it's substrate controlled. Your substrate is such a way designed that will end up with one product in major. That is what is stereospecific. And the other case is stereoselective, when there is a chance of equal opportunity of forming of two enantiomers, but you have one enantiomer in major. Okay, then which is more creditable? The more creditable is stereoselective. Why I say that? Because I have been approached with many people, even some experts. Sir, stereospecific तो बहुत अच्छा है, but stereospecific stereo अच्छा है, but stereoselective से अच्छा नहीं है. So stereoselective is you design something where there is an equal opportunity of two enantiomers, but you generate one in major. So that attracts more credibility. Stereospecific is by default substrate controlled. Is that clear? So very nice, we cleared this concept. Okay. Now what is called chiral induction then? So chirality at center A influences the chirality at the center B in the same molecule. Closer the centers A and B are, greater is the extent of induction, and we find numerous prochiral groups. That means that these centers are actually prochirals, and if you have another group in the molecules which has a capability of generating a chiral center, we call it chiral induction. That chiral induction can be induced by any part of the molecule or a molecule coming from outside, what we call as chiral auxiliary or a ligand in local terms. Okay. So induction means you induce chirality actually. So that can be inside the molecule and that can be outside the molecule. I'll tell you, how do you understand? So you will see a common understanding among students that after running a chiral reaction, they run for HPLC. I have seen students. Why? HPLC is what? High pressure liquid chromatography, right? And ये machine क्या है? What is this machine? High pressure liquid chromatography. Funda is very simple. High pressure means there is someone who exerts huge pressure, and the compound mixture passes through a column. So one side someone is pushing it, the compound mixture is passing through the column and going to the detector, and detector finds that okay, this is compound 1, this is compound 2, this is compound 3. This is way our HPLC works. Now the moment the chiral column, there is no difference. If the chiral column is packed with simple carbon C18 molecules, normal carbon molecules, they cannot identify chiral ones. They will identify different diastereomers. If the chiral packing is done by some chiral molecules, then it can understand that okay, this chiral molecule is passing through the column. And when it reaches the detector, it understands. But please try to understand HPLC. I have seen many students very confused about HPLC. There is nothing. There is someone who is injecting the molecules, molecule is passing through the column, reaching the detector. So एक तरफ से वो जा रहा है, pump खींच रहा है, detector पहुंच रहा है. The main science is in the column. I always tell my students that when you do the reaction, the main size is in TLC. TLC plate देखा है ना आप लोगों ने? TLC plate. So science is not anywhere. Science is in the TLC. If you can identify the product in the TLC, you are a better scientist. The moment the molecules pass through the HPLC column, so nothing is important in HPLC except the column. The column detects, and how does it detect? The packing inside. If it has a chiral Cephadex, it will identify every chiral molecule and it will reach the detector. So now the thing is that when you pass a reaction through such a chiral HPLC without knowing that is there any chiral induction, students go and pass it immediately. See, what you should do first, we have read that chiral molecules interact with plain polarized light. They deflect light, right? So what is your first duty? Your first duty is, if your reaction has a chiral induction, it should show a positive or negative optical rotation. There is no need of running to HPLC. Got it? So the first thing to understand as a chemist, that has there been a chiral induction in your system, can only be understood. Just do the reaction, take the vessel, take a dropper of the molecule, put it in the polarimeter, find it if there is a positive or a negative rotation. The moment you find it, fantastic, you have a chiral induction. So you have a pro-chiral substrate, you did a reaction, you got a chiral reaction. How to understand it? The best thing is passing the solution through a polarimeter, not running to HPLCs. Okay, very good. So in such cases, one diastereomer is selective, one is stereospecific, one is stereoselective. I have already explained. Okay, so these are some of the, I feel some of the important, manuscripts. I will feel some books which I would request you in your leisure time you can go through, particularly the catalytic asymmetric synthesis by E. Ojima, and this is free in online and offlines. So please go whatever is available, any one article in your time which will increase your concepts regarding the asymmetric synthesis and catalysis. Anyone, all these are equally important. Asymmetric organic reaction by Moser, even Professor Jacobson has written a fantastic article on comprehensive asymmetric synthesis. Catalytic asymmetry by Ojima, this is one of the most read articles, I feel. Very nicely written. It clears your concepts like anything. So please go through any of this which is available with you. Okay, now let me go to, okay. So this is what I started, and we think about asymmetric reactions. Just see this reaction. What is an LDA? LDA is lithium diisopropyl amide. How do you generate? You generate it very easily, right? Okay. Okay. So I write something before I go to the reaction. I've seen mentioning in the books that LDA is nothing but lithium diisopropyl amide, and you will see in majority of the cases the book has mentioned minus 78 degrees centigrade for the reaction. So I'd like to tell you that this is just an exchange. You take diisopropyl amide and put n-butyl lithium, and this exchange reaction is just an exchange of the hydrogen and the lithium ion, and this is what is lithium diisopropyl amide, and this happens in minus 10 degrees centigrade. There is no need of doing the reaction of minus 78. If this exchange happens in minus 10, then why the books report minus 78? The books report minus 78 because it goes and picks up this hydrogen. So please understand, I want to clear one concept, that generation of LDA, generation of this salt, this is what? This is a salt. This salt is generated in minus 10 degrees centigrade. There is no need of, that's completely wrong information that LDA generates in minus 78. No, LDA is generated in minus 10. In order to abstract this minus, this anion, right, this hydrogen, and creating this anion, which actually generates this lithium enolate, this happens in minus 78. So we need it. And in some cases, minus 78 is not required actually. Minus 40, minus 30 is fantastic. Okay. So this has to be cleared first. And then coming to something like competitive reactions, and you talk about kinetic and thermodynamic stability, we were discussing in the last class. And if we take that a compound like 2-methyl cyclohexanone and use an LDA, in one case you have a chances to generate a more thermodynamically controlled product. In one case we call it kinetically controlled product. And why does it happen? So why we call it a thermodynamic control and why we call it as kinetic control? Because this is a more thermodynamically stable product. Okay, and that we can do in different conditions. So this is how we explain the energy differences between a thermodynamic product and a kinetic product. And I'll just come to a beautiful example on this deuterocarmycin. If you see in this reaction, I write it in this way. A beautiful example of a kinetic and thermodynamic control, particularly in asymmetric reaction. You can see in this Dickman-like condensation, the most stable product was observed conducting the reaction under, please try to understand, conducting the reaction under equilibrating conditions for the reversible reaction, while the alternative kinetic product was observed when the reaction was conducted under lower temperature and non-equilibrating kinetic conditions. See, what is the difference? Please try to see this. This is very, very important. You have the same starting material, you use the same base, and I already showed you how LDA is generated. THF minus 78, 30 minutes. THF, same solvent, minus 78 to minus 40. And the right hand side we generate an APMR of the others. We changed the chirality, we changed the asymmetric induction. What change you find in the two different reaction conditions? This is very vital. I want to highlight you that how we are powerful, how we can control reactions. Okay, it's in our hands and here. How you are going to control it. See, same base, same starting material, same solvent, and we explain in one side a kinetic control and the other side a thermodynamic control. The kinetic control gives us 5 to 7.1 diastereomeric ratio, whereas the thermodynamic control gives you a single stereoisomer. What we do is creating a reversible and an irreversible condition. This is very, very necessary. Please try to understand. Very complex molecules, chiral centers, we just do an equilibration. How do we do the reaction? I told you that after generating the LDA at minus 10, we go down, we make it farther lower at minus 78 and add the starting material into the LDA. So it's a reverse addition. You generate LDA at minus 10, go below minus 78, then you add the starting material. And at minus 78, you rotate the reaction or you keep the reaction stirring at 30 minutes, quench the reaction there itself. And in other condition, you add it and take it slowly, leave it, warm it to minus 40. It's a warming up, okay? And it comes to minus 40 and then you put water and quench the reaction. What you are doing? You are just equilibrating the conditions. So it's in your hand. And in the process, you see, you change the stereoselectivity. So every reaction, see, it's in our hands how we use our tools. Okay. So you make this an equilibrating reversible condition and you make this non-equilibrating irreversible condition, and in the process you get a mixture of diastereomers and kinetic control conditions, and in this case you get a thermodynamic control with a single stereoisomer. Beautiful example. I have not found such a beautiful example in such type of Dickman-like condensation, which clears our concept about kinetic and thermodynamic control. Okay, is that clear? Sorry, I don't know. Okay, where this is coming. Yeah, okay. Okay, so I think this is we have discussed. So this is a pro-cal center. Yeah. Now coming to the next part. So we discussed about FGs, functional groups, but just come to the point where I would like to highlight something. You all know what are this. I think you know this you are knowing from class 12 chemistry maybe. This is what an aldehyde or a ketone, right? You have been writing it for long, and if you just use a protonation or an alkylation, you generate in the process like oxocarbenium ion, right? And then this is also known to you depending on you have one hydrogen or both alkyl groups, and you can call them as an aldimine or ketimine, basically they are imines. And the second one, you also generate or activate this imine with a proton with an alkyl, and you call it iminium ion, right? These are functional groups, most versatile sources of electrophilic carbon. So we need electrophilic carbon in synthesis and every type synthesis, everywhere we talk about this. But I would like to know you, which is more electrophilic? You tell me. Which is more electrophilic? Again your sense of toolbox comes in. Which is more electrophilic? Why it is necessary? Because you need to choose that what would be your starting material. Very simple question. These are 4 and all these have electrophilic carbons. What I want to mean. Aldehyde, ketone, oxocarbenium ion, aldimine, ketimine, iminium ion. I would like to ask, what about the polarization? Because we know we have been reading about this carbon positive and oxygen negative from our class 12 chemistry, and do we have a quantification where we would like to highlight that which one is the most electropositive one? What is your opinion on this? Which is going to be more electrophilic, most electrophilic? Okay, I give you a quantification. So this is what is a calculation and gives you the partial charges, okay? As familiar, as we know all these polar resonating structures, and we find some molecular orbital calculations, and they say that the delta positive in case of iminium is 0.33, and the delta positive in case of carbonyl is 0.51. For an iminium ion, it's 0.54, and for an oxycarbonium ion, it's 0.61 when R is H, and 0.63 and R equal to methyl. So now you tell me that why it is necessary. It is necessary because if you want to go for an electrophilic addition, a nucleophilic addition to a carbonyl, then this gives an idea that which one you should take. Because I have seen students coming to me and saying, sir, इसमें reaction मिठा रहा है नहीं जा रहा है. You want to go for a nucleophilic addition to a carbonyl and the reaction is not going with a nucleophile. So what should you do? Will you go on repeating the reaction 100 times? No. In that case, these minor details are necessary for our reactions, and in the process we go towards asymmetric synthesis and catalysis, and this gives us a clear identification that if we want to have the best activated carbonyl, then as per this ab initio calculation, the oxocarbenium ion is the best one. So if you want to do a reaction and you want to add a nucleophile to an activated carbonyl, then this activation, this proton activation, which gives you the highest delta positive, is the best one. You should not choose an imine or you should not choose an iminium ion. Rather, you should take the carbonyl and activate it like a proton activation. So the electrophilic potential of the C or a carbonyl functional group may be greatly increased by either Lewis acid coordination or protonation, and the magnitude of the increase is about 10 to the plus 6. So we have been telling it. We have been telling it that we have been showing that Lewis acids being coordinating with carbonyl, but where is the quantification? So we need to know the quantification, we need to know the facts. The facts is this, that this is much more activated than an iminium one, okay. So if we want to do a successful reaction, we want to do a successful nucleophilic addition to a carbonyl, the best way is you activate the carbonyl. This is the best one. Don't try with iminiums. Okay. There are other things of conditions as well when we feel that we want to go for nucleophilic additions to carbonyls. Why we are studying this? We are studying this because this is where we generate enormous number of asymmetric molecules. In this concept, we should also understand that if the nucleophile maintains an 107 degrees, or which we call it as Dunning-Burgi trajectory, this angle of attack has to be maintained as well. So the first thing is an activation, and the second thing is attacking of the nucleophile with a perfect trajectory is very important for such additions. So as a chemist, we should always remember these considerations, very, very important. Okay, now comes to the next one. So what about C double bond O versus and C double bond OR plus? Any idea or any quantification on that? Yes, we understand. We understand that the LUMO coefficient, what we show in the slides on carbon for B, will be considerably larger than that of A. Does this mean that there is a lower constraint on the average of angle of attacking nucleophile? There is absolutely no experimental proof for this question, but it is worthy on consideration. I will also come to some others one by one, where you will find that there is a change on what concept we have already read through. Okay, I'll skip this and come to the final. Okay, this one. This is, I think, one of the most fascinating understandings of of intermediates that we have been dealing in day-to-day life. Particularly when we talk about C double bond O addition. See, simple reaction. If you take a carbonyl, for example, and formaldehyde, and have water in the system, you generate a coordinated transition state, and this can be a T1 and that can be a T2. This is what shown by Schoen in Jackson 1983, and he completely says with this theoretical consideration that we will have an intermediate where the carbonyl is actually attached to one molecule and gives a 4-membered transition state, whereas there can be a possibility which is of much lower energy and having a similar transition state or activation of the carbonyl with 2 molecules of water. See, this is what was proposed in 1983, where he was discussing only a simple concept of carbonyl hydration, nothing else. But what was the impact? I'll show you. So just correlate this proton shuttle. Proton shuttle means you have a carbonyl, you have water, it attaches the carbonyl and releases back. And on the other side, we all know about Grignard and Barbier-Grignard reactions, where we think that the alkyl zinc or magnesiums attack in this carbonyl. And I will just highlight one important information, what the scientists have observed, that catalytic amounts of zinc iodide dramatically catalyze the addition process. As a student, we need to correlate these two observations, very, very important. See, when we hydrate a carbonyl, we talk about 2 transition states, one is 4, one is 6. One involves 1 molecule, the other involves 2 molecules. When we come to Grignard and zinc addition reactions, we find that addition of zinc iodide, it's very easy, right? It's just attacking of or formation of an O zinc. So then why addition of zinc iodide catalyze the reaction? What is the implication? See, why this is necessary? Because carbonyls or addition of nucleophiles to carbonyls is the best used or best explored reactions in academia and industry for creating asymmetric centers. So although this information is very small, but what are its implications? The implications is that what we have been reading in case of carbonyl activation is not correct. The main reason is actually there is a formation of a 6-member transition state. It's not the way that we show RCO ... zinc. No, that's not the actual intermediate. If that was the intermediate, then addition of zinc iodide could not have dramatically increased the reaction rate. So that is why I asked this question, does these results relate to real reactions? What does it mean? I mean that whenever we have showed this zinc or magnesium catalyzed reactions, we write it in a very simple way, carbonyl ... zinc, and there is a nucleophile which is attacking from the carbonyl and making the reaction. We have been reading it throughout, but actually if you see inside the reaction and understand it, it's just nothing. All this is actually going through, the carbonyl activation is actually going through a transition state where there is an involvement of two molecules of the activator in case of water and also in case of organometallics like zinc. So this is the actual bimetallic transition state or involving two molecules. I'll also tell you the story of the Grignard reaction. Okay, the same thing happens with boron and also aluminium. In all such cases is just 6-member intermediate. It's not the intermediate that we have been reporting. This is also proved. So we have proved these reactions, we have experimental proof, numerously reported that it's a 6-membered intermediate which is actually activating the carbonyls. Now, what is this reaction? This is a reaction that we have been reading from our class 10, I think. What is this? It's a Grignard reaction, right? So Grignard reaction is something like you add alkyl magnesium bromide to a carbonyl to have this COMgBr. We write this, right? We have written all throughout our lives that this is what is a Grignard reaction. You take magnesium, add alkyl iodide, and the reaction goes like this, and it forms ROMgBr, put water, and you then get the product and alcohol. We have been writing this. This is absolutely wrong. The actual thing is this. The actual thing is something which we have not encountered, not seen, but true, which is the Schlenk equilibrium. And this completely suggests that a reaction happens, or the Grignard reaction happens better in solvents like ethers. They don't happen well when you take the solvent as THF, tetrahydrofuran, which is also an cyclic ether. And it happens to be fantastic when you take diethyl ether. See, THF, cyclic ether, diethyl ether is an alkyl ether. But numerous examples where the reaction of the Grignard reaction has not worked at all, 0% yield in THF, whereas 90% yield in diethyl ether. Why it's happening? It's happening because this one, what has been reported, is completely wrong. It's actually the Schlenk equilibrium, and it involves not one magnesium. It involves actually 2 units of magnesium, and it goes through a dynamic equilibrium like this, and here S is nothing but the solvent in which the reaction is happening. And as the diethyl ether is an aliphatic ether, it easily coordinates and gives a very good stabilization of this intermediate in Grignard reaction. Whereas when you take cyclic ethers, 6-membered, 5-membered ethers, this type of intermediates are not formed. And that's why, these Grignard reactions happen to be very well in diethyl ethers, but they fail in cyclic ethers. This is only explanation which we can give you when we think of this type of equilibrium, which is the actual transition state when we talk about these Grignard reactions. But you just remember that we have been always writing this reaction, putting a proton and then just cleaving the OMG bond and giving the alcohol as a product. Okay, so why this is necessary? This is necessary because we need to understand what type of intermediates are actually working. Otherwise, you cannot induce the chirality. To induce chirality, we need to understand what is the actual intermediate of the reaction. So, So there is a huge difference what has been proposed all the way along and what's actually happening through a Schlenk equilibrium in case of a Grignard reaction. Okay. Now, this is one thing. Okay, I found this, that although there was a Schlenk equilibrium we have been proposing, where is the proof? And there is a proof. This was a report in JOC by 2002 by a Japanese group, Yamazaki, where actually he was successful to get the single crystal X-ray structure of this type of an intermediate. Beautiful work in JOC. He has actually seen that there is solvent coordination, and he has isolated this intermediate, and not even that, he has also solved the X-ray crystal structure in this paper, who has clearly proved that actually this is not the intermediate. This is actually the intermediate in a Grignard reaction. Okay? Fantastic. Okay. Now the last part, what I would like to highlight is coming to the original one, that when we create chiral centers, how well we are equipped with the knowledge of utilizing our toolbox. Okay. See, this is something which Dobbin reports in 1956 in JACS, and he says that if you have a simple molecule like 4-tertiary butyl cyclohexanone, and you want selectively one of the diastereomers, then actually you can choose your reagents. You see, he have given a fantastic graph, and he shows that when he uses diabal in this case, then actually the ratio of the actual diasterone isomer is 72, whereas if you use selectride as a reducing agent, it's completely reverses. Why this is important? See, there is no such group close to the carbonyl so that it can induce the attack, but actually you are choosing different reagents. So this study by Dobbin supports that you should not require anything closer to the prochiral group to control the stereoselectivity. That's not required. Okay. What is required is your actual knowledge of the toolbox, and which is reagent list. Because this clearly understands that when you take diabal, then the actual is 72, whereas equatorial is 28, and when you take selectride, it's just reverse. There's a huge differences. So this gives an idea that if you have a simple carbonyl and you want exactly the equatorial one is the major, I can choose the perfect reagent to do it. There is no need of something called the substrate control. That's not required. And there are numerous examples he has shown where there is complete reversal of stereoselectivity. Okay. So here comes the way to understand that how we approach the product development and the steric approach control. Okay. So I stop it here, and although I have some more slides, but I will post you up. Let me come up with one small tutorial, because this is actually for the tutorials. I had many slides. So now, what type of product you can think of in this reaction? Can you just draw? Okay, I'll come to the product. So if you have a reaction like an LDA with an benzaldehyde, it actually forms a reaction the way I have shown. So you form an N-butyl lithium, you take N-butyl lithium and form an LDA and generate the enolet, and through all these steps you go up to the product. Okay. Now the second one is just a small base catalyzed reaction, and I want to know you what is the name of this reaction and what is the reactive intermediate involved in the reaction. What is the name of the reaction? Okay, so it's something like a Dickmann condensation, what we discussed regarding this, and the intermediate is an enolate. Okay, is that correct? Okay, very good. Now the third one is a reaction where we use a substrate which has two esters in both the sides, and we have a base called sodium methoxide and protonation, and which one is the correct product and why? Okay, anyone from this side? Which one is the correct product? So it's C. Okay, anyone from this side? Okay, let me see. So it's not C, it's actually B. Okay, and we do it in this way. Okay, got it? Fine. Okay, now the last one. So product like A. So what is the product A? Okay. Then we go for a second alkylation. Then we do a aqueous NOH and water or protonation, and then we heat it and we get a decarboxylation. I want you to predict which is A, which is B, which is C. Okay. So, okay, I don't know this. Oh, sorry. Yeah, okay. So we go for a first alkylation. We have ethyl butyl acetoacetate in 69 to 72%, and then we go for a second alkylation, and then we go for sodium hydroxide, hydroxylation, and finally decarboxylation. Okay, so this is just examples. What we plan for examination tomorrow. So I think at the end we are conducting an examination. The examination will have multiple choice, and we'll do the grading and give you certificates on that. Okay. Okay, I stop it here. Thank you very much. And I think tomorrow we have Oliver's class in the first, and then I go for organocatalysis. Okay. Thank you. Okay.